All right. So for which textbook should I? Yeah. Hello. Hello. Oh. Hello. So, so we're going to be solving questions from this. About, I'm trying to bring it up. Please bye bye to the habits. That to make mix. That's to the bye bye to make mix. Wash my hand clean from it. Now you have to draft it. You have to draft it. Okay, so let's do this. In a certain process, 8 kilocal of heat. Now I'm writing seriously and solving. In a certain process, 8 kilocal of heat has been transmitted to the system. Yes. While the system does 60 kilojoule of work. While the system does 60 kilojoules of work back. While the system does 6 kilojoule of work. You got it? They are not looking for anything. They are saying by how much does the internal energy of the system change during the process? Yeah. So have you gotten the answer? Now watch. In the setting process, in the setting process, so in the setting system, right there, the setting process, 8 kilocal of heat, 8 kilocal of heat, 8 kilocal of heat is furnished. So let me stop. Let me stop. Let me stop. 8 kilogram of heat is furnished to the system. Why the system does 6 kilojoules of what? Heat. I mean, okay, by how much? By how much does the internal energy of the system change during the process? By how much does the internal energy of the system change during this process? Eh? Eh? Yes? Uh, you can get the specific heat capacity of water. Okay. 4,200. So we have it 4,200. We have it 4,200. Specific heat capacity of water. That one is joules per Lewis per joules. I don't. By how much does the internal energy of the system change during this process? Use the value in the question. You can use specific heat capacity to calculate the Q. The Q. You know, you're working with thermodynamics equation. You're working with thermodynamic equation. Huh? No. Are you? Let me see. In a certain process, yeah? Yes. Yes, why? Let me off. Okay. Let it be later. Read that for me. Call it out for me. Please talk very well, I beg. 8 kilogram, be 800. 8 kilogram. You converted. 8 kilogram. Yeah. This is the question I just read out. In the same process. 8 kilogram, yeah. Yeah, continue. So, specific capacity. Yes. My brain is scattered. Oh no. The ones are never arranged. Yeah. What did you say? Call it, call it. Yes. Does what? Eh? So wait. They had 8 times 1,000 specific capacity. What about those other things? No temperature change. No temperature change. Yes. What else? Eh? Multiply these two. That is MC. You get? Yeah. 4,200. Yes, it, that was the that was the capacity. Q. That means this was the amount of heat that was getting transferred away from it, maybe towards another person or something. So what the question asking? By how much? By how much do they the internal immune system? Yes. I see they just utilize the best brain. Let's move, let's move, let's move, let's move, please. So after that, what's the next in our equation? I know yeah, minus work. Yes. What's not the work of heat is furnished to the room? Why the system does 8 system does to the okay, right. So what do we have next? Oh yeah. From here I'll be having 2,000. This work is even right. I said the specific capacity of water is 4,400 joules per kilogram. Did you hear me? By how many joules does the initial energy of 50 grams of water change? By how many joules does the initial energy of by how many joules does the entire energy of 50 grams of water change as there from 21 degrees Celsius to 37 degrees Celsius? Alright. Assume that. So, have you gotten the answer? Christine. Also, your specific capacity was 4,000. The mass of the water is what? The mass of water is 50 grams. $3,000. Yes, that's correct. That's correct. Next question. How much does internal energy how much does the internal energy of 5 grams of rice of rice 5 grams of ice at precisely 0 degrees Celsius? Clearly. How much does the internal energy of how much does the internal energy of 50 grams of ice at precisely 0 degrees Celsius increase as it is changed to water at 0 degrees Celsius? What is it? Is it? What's the answer? Joe. Alright. Admin. 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 Let me call her. The hotspot. So the question says what? How much does the internal energy of 5 grams of ice at precisely 0 degrees Celsius? So I am having 5 grams like this. And that 5 grams, when you convert it, that's how many kilograms? So mass be what is internal energy of? They gave the value for the latent state of fusion. 80 calories per gram. Yes, 80 calories per gram. There's no need of converting this one to kilogram. Let's work with it. Yes. The final answer. No, 0.4, 0.4 what? Units. Units. Those 0.4 calories. I said the specific capacity is 80, 80. 80 times 5, maybe 400. Times 5, that's the mass. To do what? No. Have you gotten it? You've gotten it, have you? Guinness myself. Ava, the question. I want to use myself. All of you. I mean, no, I'm using just one minute. I'm in the app before. So, we'll continue with our questions. So look at this one. Find all right. So we have a number of questions to treat. And we are going to pick number one. One mole of an ideal gas one mole of an ideal gas undergoes an isothermal expansion. Sorry, I was moving up to check other questions. Sorry. One more. Yes. One more of an ideal gas undergoes an isothermal expansion at 35 degree Kelvin. 35 degree Kelvin. At 350 Kelvin. From 0.02 meter cube to 0.08 meter cube. Calculate work done. Sorry. Three moles of an ideal gas. 3 moles of an ideal gas expand constantly from 4m3 from 4m raised to the power of 3 raised to the power of 3. 3 moles of ideal gas expand at constant pressure from 3 million to 5 million. From 4 meter cube. From 4 meter cube. From 4 meter cube to 9 meter cube under a pressure of 1.2 times 10 raised to the power of 5. There's no temperature, just pressure 1.2. But they give CP. CP is equals to 29.1. Then you say you can get it. CP. CP is 29.1. Letters are not even arranging in my eyes. Hmm? It's not arranging in my eyes. Right. It's not. Have you solved it? You almost solved it. It's behind because I know very English. Yeah. So what do you have? 3 moles of an ideal gas, eh? Expires what? Expand isothermally, eh? From at the pressure of what formula are we using? Yeah, tell me. What formula are we using? That's not telling me, I'm not processing. All right. 3 moles of an ideal gas. Ideal gas, right? What happened to him? Expanded down. It's a thermal expansion. Okay? Okay. SCP is what? So what we're going to do, work done in a gaseous system is what? In a gaseous system is what? Work done in a gaseous system. What's the formula for work done in a gaseous system? Yes? Right? And then we're giving everything now. So, where's the email? Where's the email? Okay. What are we doing? What is it? 600,000. Yeah, no. That's the only thing he has for him. That's the answer. Yeah. The next question says, the next question says, one mole of a monatomic ideal gas undergoes the following. One mole of a monatomic ideal gas undergoes go. Yeah. One mole of monatomic gas undergoes the following sequence. As, as a baric expansion from 2 meter cubed to 5 isobaric. From 2 meter to 5 meter cube. Isochloric cooling. Isochloric cooling. Yes. Please wake me up immediately. If I sleep, wake me up immediately. Immediately. Yes. Secondary. I just say that. Yes. Then isothermal compression. No. Isothermal isothermal compression back to the initial state. Calculate the total work done during the cycle. Calculate the total work done. Alright. Admin your network. Let me read it. One mole of a mono question says, the question says, on dates. Hello. So, what's the read out the question? One mole of, so we have one mole of monoatomic ideal gas, yes? What are the things you have to use? I can't hear you. But have you attempted it? Attempt it. There's pressure you mentioned. Hello? No? What's this girl? My phone. My phone. But the network is not connecting. It's connected. Yes. Do you have it? Do you have it? I need to confirm. Okay, they didn't give pressure. that first one, she really said it was an isobaric expansion. So, but the fact that it was isobaric, I don't think we're going to be expecting to. We might leave the answer in terms of the pressure. So for an isobaric process, what's happening? What's happening? W is equal to PV2 minus V1. What are our two distances? What's the next thing they told us? Isochondric is 0 now. Work done is 0. For isochondric, work done is 0. Work done is 0. No, like isochondric. Isothermal, you know that this P change in V, I'm coming. Isothermal, we usually write it like, we know that, listen up, we have nRT. Number of mole is 1. Then our R is what? This is why I'm getting these joules. Are we giving time? Are we giving time? Because what is it? Let's solve it as a temperature. So V2 over V1. What's V2 over V1? So W is now equals to what? 7.61 watts. 7.61 watts. Temperature. Which one is that one? What are they doing? Okay. So that means it's a what? So what's the Yes. So you're having total pressure, total work done is equals to what? 3P plus 0 plus 7.61 T. Okay? So that's it. So next question. Sharp. So we solve again. Okay. A gas initially occupies 0.03 meter cube at 250 kilopascal. At 250 kilopascal, it expands adiabatically. It expands adiabatically. To 0.08 meter cube. 0.08 meter cube. 0.08 meter cube. Given y is equals to 1.4. Yes. Given that y is equals to 1.4. Determine the final pressure. Determine the final pressure. I'm not giving anything. I'm not giving anything. So to get this, you're using that your P1 V1 equals to P2 V2. Just that your V factors is going to be raised to the power of Y, exactly. So that's what you're doing. So we're having no, even if you leave that to give it the same answer, since we're working this thing. So what do we have? So from there, what do we expect? What's going to be the answer? Good. Okay. A Carnot engine operates the Canon engine operates earlier. The Canon engine operates between temperature of 650 Kelvin. Yes. So 650 Kelvin and 310 Kelvin. Determine its maximum efficiency, heat rejected if it absorbed 1,800 joules. Heat rejected, yes, if he absorbed 1,800, then work output. So how do you get that one? For your Carnot, what's the formula for efficiency? Okay. So you can work that out. What would that one give you? What will it give you? 22.3%. So 0.52 and percentage, that's 52%. Nice one. Yes. Yeah. What was it? Calculating what? So now, calculating the heat rejected. Efficiency is equals to work over the work operated by the QH. So QH is that amount that they give to you that they have removed. Yeah, 1,800, yes. No, you use it in decimal, you can't use it in percent. Correct. Have you done the last one? All right. All right. A refrigerator. The refrigerator removes 750 joules of heat from the cold reservoir using 250 joules of work. Yes. Yes. What is it? All right. Oh, yeah. Okay. Um, a power plant has an efficiency of 35%. A power plant has an efficiency of 35%. If 5.5 times 10 to the power of 8 joules of it is supplied every hour, 5.5 times 8 times 10 to the power of 8 joules is supplied every hour. Determine, determine useful work. B is wasted. Have you gotten it? Have you solved it? Hmm? Okay. Yes. What about the heat wasted? How about the heat wasted? I didn't hear you. No, 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 no. Yes, it turns power of 8. jump that question. I'm coming. I'm coming. A gas initially occupies a gas initially occupies a gas initially occupies 0.03 meter cube at 250 kilopascal. Yes. It expands adiabatically. It expands adiabatically to 0.08 meter cube. Given that by given that y equals to 1.4, determine the final pressure. Determine the final pressure. That's all it before. A gas follows the process P equals to KV squared. P equals to KV squared. Where K is equal to 4.5 times 10 to the power 5. The gas expands from 0.2 to 0.5. The gas expands from 0.20 to 0.50. Meter cube. Yes. Determine the work done. It's for volume. It's for velocity. For velocity. Sorry. Velocity, yes. Okay, sorry, body. Yeah, let me confirm. What do you guys give? 40,000. No. No. Is in this one, it's supposed to do this. It's supposed to integrate. Hmm? I gave you the function. I said it has to use that process. So people that are partner side is that people going there. Yes. That's what. So what's the issue? You're looking for work done. Work done is the integral of that function. Since velocity is changing there, so it means you can. To me, velocity is changing. Work done equals to work done is equals to what? Pressure and change. Since they change the volume, you integrate that with respect to change the volume. And then you'll be having what? You'll be having V cube over 3. Yes. All right. What's that? 4,050. Okay. For the work done, because I made a mistake. You didn't incorporate after getting that your integral value. Did you later? Okay, let me just solve it. Read the question out for me. Yes. Stop there. It simply means Shebi is work done they want us to get. So if I'm going to be getting the work done, you need to appreciate that the work done is equal to the integral of what? P change in what? V. True or false? Which I can write like this now because I want to integrate it. Right? And I'm moving from V. And now V final in this question is what? 0.5. I'll just call it V2, V1. True or false? Can this thing integrate here? Okay. Then it's equal to what? P integral of what? True or false? Now, the question there, that's our normal expression, right? But they gave us an expression here in that question. Where is it? Where? Thank God. They said it equals what? KV square B. So this same approach we use, we'll use it for that one. KV square B. If I take the integral, I'll be having KV square. Yeah, I'm having what? I can't hear you. V2 and what? And V1. True or false? So what will I be doing from there? Did they give us the value of our K? What's the value? So if I'm integrating this, it's giving me running from 0.5 to 0.2. Right? So that means that we're having this now. What's the value of K? 5, Abby? 4.5 times 10 is power of. Is it minus 5 or 95? Is it minus 5 or 95? Like this. What are we going to be doing? Divided by 3 and 0.2 divided by 3. Right? So W now is equals to what? 4.5 times 10 raised to the power 5, open bracket. What does this one give us? 0.5 cubed. To make this equal, 0.0 what? That's sure. Minus everything inside here. When you multiply it, what does it give you? That's the answer now. So where you get your answer from? 17,000 watts. Okay. So, number next, let's hit more question, right? That's what I'm working. But when I do hungry, the questions relax. These questions will happen. All right. Chima, you ready? The gas expands adiabatically. The gas expands adiabatically. Performing 950 joules of work. Performing 950 joules of work. Find heat transfer find heat transfer and change in internal energy. Find heat transfer and change in internal energy. And then, which are religions? The religious question notes. And then, that's very direct. There isn't the thermodynamic equation. Change in U is equal to what? Q minus, that's Q minus W. I mean, what kind of a thermodynamic system is this? Adiabatic. In an adiabatic system, Q is 0. So we are left to change U equals to what? Minus what? W. That's it. And they're not asking you for heat transfer. Heat transfer is zero now because they're diabatic. It's not something you solve. You understand? Heat transfer is zero. They just put that to trick you. You start solving what you can never get. Even if you eventually get, you get zero as answer. That's the way. Yeah. Yes, negative 950 joules. What does the negative imply? I didn't hear you. That means the system was using, that the gas was using 950 joules of its internal energy to perform work on the surrounding. That means the work there was not work done by the surrounding, it was work done by the system. Do you understand? So that's it. Keep the spirit high. Let's go again. Ava, tell her I need lozenges. Tell her I need lozenges, my truth. Let's go. Let's go. It's happening. Let's go. A gas obeys the pressure volume relation. A gas obeys the what? Pressure volume relation. P equals to 6.2 times 10 raised to the power 5 V3. Yes, V3. That's VQ, V3. What I call for you now? V what? VQ. Right. P is in pascals, V is in cubic meters. The gas expand from V1, which is equal to 0.15 meter cube, to V2, which is 0.60 meter cube. Question now is, determine the work done by the gas. Determine the work done by the gas. So I look for work done by this gas. That's what? I don't get it. Any what? You're asking me. Hello? What did they ask you? You know that the original standard of work done is pressure multiplied by what? Change you. But they are now giving you an expression for the pressure that they are telling you it works for this question. It means the work done now is equal to what? 6.2 times 10 raised to the power 5 V cube dV. I mean, then I want to get the work done value. What am I supposed to do? I need to integrate this. I need to integrate it. So when we integrate it, what do we have? So I'm saying our work done is equals to make things easier, bring out this guy, right? Ten to the power 5. Then inside here, we when you integrate it, let's say you integrate it here, can I even put that integration at front? Integrate it here. What do we have? V4 over 4 bounded by this, Abi, upper limit of 0.6, lower definite integral. So what do we now have? So what do we now have now? On what? 6.2 times 10 to the power 5 into big brackets, yes. 0.6 over 4 minus 0.15 to the power 4 over what? 4. Help me, what do we now have? Everything inside the bracket, give it to me. Everything inside the bracket, give it to me. 0.0, that's everything all together. 0.0. When you multiply, what's the answer? Now we are going to join. Okay. Listen. Oh. Right. Four moles of an ideal gas. The question: 4 moles of an ideal gas are heated at constant volume. Its temperature rises. Its temperature rises from 290 Kelvin to 690 Kelvin. 290 Kelvin to 690 Kelvin. Given that CP, specific heat at constant pressure, CP is equal to 29.8 joules per mole. Are you there? 29.8 joule per mole dot Kelvin. find CV, comma, the heat supplied, the change in internal energy, and the work done. And then it's under a question. This is a question. Because we have been able to complete everything from our module 1 in this event. We've completed from module 1 down, successfully down to module 14, if I'm not mistaken. But what? 15, almost half of it. We are going to be running massive questions. Today is going to be like this morning, it's going to be like a carnival drive, solving multiple questions on these things. Because physics is about application, we'll keep solving and solving and solving. So from this one, I'm going to be driving us into dynamics and fluid mechanics kind of questions to set your mind tuned with viscosity issues. Let's move. Let's go. Yeah, easy work. Thank you. How are you going to help us find CV first? Remember that CP over CV is equal to what? Yes, thank you. It's Y, but did they give us Y? So what else can you use? You are not aware that your CP is equal to CV minus R. You didn't know? CV plus R is equal to CP. See, that is why you are here. Learn it now. Are we together here? No time to waste, no time to drop seconds on the floor. Let's move. Yes, so our R is that 8.314. So we are saying that we've been able to establish CV is equal to CP minus R is a true equation. Thank you, accurate. So from here we are knowing that CV is equal to, what was our CP value again? 29.8. You have 29.8 minus 8.314. And that gives us sharp. The marker is dead. No worry. Let's move. So yes, where are we? Heat supplied. Did they give us the temperature change? What's the temperature change? So our temperature change is what? 690 minus, giving us what? 400 Kelvin, right? Now, heat supplied to the system. Where will our mind go to? Somebody help me. Thank you very much. That's the spirit of science. NCP delta T. NCP delta T. That's the heat supplied. NCP delta T. Are we together there? Okay, so you have, let's put our values. Oh, hold on, let me ask you a question. Why not CV? Why use CP? At constant volume. Read your question very well. That is why you are supposed to use CV. Because the parameter you have that is not changing, that you will work on, that is not going to be altered, is that V, volume. Do you understand? So good. So H is equals to what now? How many moles are we dealing with here? 4 moles, sharp. Then our CV is what here, please? 21.486 multiplied by 400. What's the value? 34,377.6 joules sharp. What they ask us to solve again? Now, what kind of a system is this? Volume was constant, true or false? So we will first of all establish the fact that this system is an isochoric system. True or false? And in an isochoric system, what is the effect on the thermodynamic equation? It makes us W is now equal to what? 0. Therefore, change in U is equal to what? Q. Thank you. Do you grab the gist? So that means that change in U is what? 34377.6. Yes. Let's move. Let's move. Now, this particular question says, what's my time on this one? Now we're moving into the base. Look at this question. A cylindrical tank contains oil of density 850. A cylindrical tank contains oil of what? Density 850. 850 kilogram per meter cube to a depth of what? To a depth of 8.5. Determine the pressure at the bottom due to the oil. My question is this: how does pressure act relative to depth? The more you go deeper, the higher the pressure. The more your height increases, the lower the pressure. Pressure at higher altitude is what? Low. Let's move. So A says, the first part of the question says, listen up. The first part says the pressure at the bottom. Second part, the absolute pressure at the bottom if atmospheric pressure is 1.013 times 10 to the power 5 Pascal. Yes, at the bottom, they will do absolute pressure. Then part 3 says the force exerted on a circular base of radius 0.80. SI for radius. SI meters. So that first one they're asking you for, the pressure at the bottom due to the soil. Pressure at the bottom due to the oil. What do you call that pressure? That's like gauge pressure. That one we are not including atmospheric pressure inside, two of us. So that's gauge pressure. What formula are you using to calculate that one? Sharp. Yes. Pressure is equal to rho G H. Are you sure 72? What are you using? 10? Okay, maybe that's the reason the difference. Let's use 9.8 all true. Use 9.8. Okay. So how the density was what again? Help me. 850. This one is 9.8, and then we're having 8.5, giving us what value? 70,805 Pascal. All right. Second one, absolute pressure. What's the formula for absolute pressure? I didn't hear you. The absolute pressure, listen to me. The absolute pressure, P absolute, is equal to atmospheric pressure plus the gauge pressure. Hope you know you have got your gauge pressure. And you know your atmospheric pressure. So you just put them together. Pascal and Newton per meter square are the same. They are numerically the same. Like 1 Pascal is still 1, not atmosphere, 1 Pascal is still 1 Newton per meter square. Do you get? So P absolute is equal to, we have in there 1.013 times 10 raised power volts 5 plus 70805. What's that the answer? 1. Okay. What is the force on the base? What is the force on the base? What's the formula for force? Thank you. Pressure times what? Area. Good. Yeah. First at the bottom, we'll look for the area. So what's area? Very good. What's the R? So we're having 3.142 times 0.8 square. Thank you. 2.011 times square. Yes. Thank you. I see this one. $380. All right. All right. Let's move. Water flows through a horizontal pipe. Water flows through a horizontal pipe. Water flows through a horizontal pipe. Diameter decreases from 150 millimeter to 60 millimeter. 150 millimeter to 60 millimeter. Velocity in the larger section is 3 meters per second. Determine velocity in the smaller section. Yes, that's A, the velocity in the smaller section, and B, pressure difference. Pressure difference. Mm. Oh. Oh. Oh, police. Oh. I need Los Angeles. My voice. I need Los Angeles for my voice. Scholars. Have answers drawn. Trouble matter is that we don't only the area. It's a long thing. You can work with that eventually the pie in the two areas you are looking to cancel out. So we can just work with the fact that the diameter goes square. Like even the fourth division will cancel out. So it's only that square effect on the diameter of the day. You will get what I'm saying. What's the diameter? 60 millimeters. Yes, okay, in question. So that means what are you looking at? Continuity, Abby. Continuity where pause first. What's the equation of continuity? According to continuity, A1 V1 equals to A2 V2. Abby, and we have derived our scope. So I use our own V1 squared V1 equals to what? V2 squared V2. Who they look for go? So therefore, V2 would equal to what? D1 squared V1 over D2 squared. Are you getting me now? So, what is V2? It was the what? It will cancel out now. You need to cancel out. It will cancel out. Okay, I'm coming. Sorry. Yeah, Chief. have dropped. People have gotten the answer. Give me values. Give me details. For which one? Velocity. Continue, sorry. Velocity was what? 0.75. Abi? Meters per second. Which other one again? That pressure difference, who help us get it? It's Bernoulli. It's Bernoulli. Are you getting me now? Whenever I see a question like that, you should think Bernoulli. How? Bernoulli makes you understand that the P1 plus, I get me now, plus the 1/2 rho 1 V squared. Are we together here now? If I don't need to put the 1 here on the V, because the material, the fluid is the same. It's the same fluid that's flowing through them. The density is the same. Will be equal to what? The same thing, but this time around, P2 plus 1/2 rho V2 squared. Should be the answer for the pressure difference. Have it? Pressure difference now will be equal to what? Carry this P2 to this other side. So P1 minus P2 will be equal to what? 1/2 rho V2 squared minus 1/2 rho V1 squared. Are you with me now? Let me jump. What we are looking for is a scalar quantity. So the sign does not matter. Even if you add minus, you would. You worry too much. You worry too much. That was the problem of Jesus Christ's disciples. Read your question from the beginning. They gave you density. That's the first thing they wrote. It's okay. Your first statement was what? Did they give you density? Thank you very much. Thank you very much. As water is the statement. Density now waiting. 1,000 sharp. P1 minus P2 is now equal to what? So that we don't press many values, you can just collect, factorize. I mean, I'm having equal to 1/2 density. Then we're having what here? V2 squared minus V1 squared. That's 500, yes. What are those values? The velocities, which one is the 3.75? Minus waiting. Final answer.
The final answer is 171.
200 and what? Sharp. Sharp. Let us pick a question from the venturimeter. What's the problem? What's the problem? Sorry for you. The venturimeter, it works on the principle of Bernoulli. Yes. After the venturimeter, when you touch Torricelli, let's go. A venturimeter has diameter 120 millimeter and 60 millimeter. A ventrimeter has diameter 120 millimeter and 60 millimeter. Let me tell you what a ventrimeter looks like. It looks somewhat like this. You guess? This is the truth. This region here is the truth of the ventrimeter. I get me, that's the truth of the ventrimeter. The pressure difference is 45 kilopascal. The pressure difference is 45 kilopascal. Determine the discharge. Determine the discharge. We call it the way we call it from where you are from. Discharge. Which one is discharge? The discharge, which must vibrate. Let's go there. Oh, yeah. Oh. So what do we have? They've given us the pressure driven direct. Okay? So since they're giving us pressure driven direct, you know what we are left with. Now they said the ventrimeter has diameter that. They've given us pressure difference. Determine the discharge. Okay, what do we do? Based on the Bernoulli. Thank you. The change in P. Solve. Solve. Somebody will have like, you not give me any velocity. Can they see something we can do? Can still do things. Yeah. That's the type of question that we shoot in the exam when you're sure that it will not pass like 5. Forget this one. Now, look at that question. As they not give you the V, now you are going to show the question that you are the creator of the V's. Now let's do something. See something. See something. Maybe this is your intention. See your clear intention. Normal, your clear intention was to do A1, V1 to be equal to what? I lie. That's your intention. True or false? True. Now, how about we don't worry too much about that and we just focus our energy on what we have? That's one thing. See, why in physics, you have to work with what you have and leave the rest to Jesus and watch him do his miracle in front. I didn't hear you. God, is marking and putting in my mouth. What do I do? Yes, you are still worried. Oh, yeah, now. Oh, yeah, so that's why using that D1 square and D1 still good. Oh, yeah, now. So D1 square, D1 square equals what? D1 square now equals what? D2 square, D2 square. You are seeing that I can.
the D. Sorry, I'm putting here. Abi? What do you think I want to do? Do you have a plan? See your confidence. Because I told you I have a plan. You see it. You are thinking now. So look at something. This one now. What's the value? What value? 120, Abi? For which one? For this one? We can put it for anyone. 120 square V1 equals to waiting. 60 square what? Oh yeah, what do you not do? You are too slow, my sister. You don't know it before. Don't tell me that's what you're doing. You're doing. Look at CMAS. 120 square over 60 square equals to waiting. Leave that V1 there, get Y equals to V2. This here is not the same thing as 120 over 60 square like this. Why do you like big numbers? Engineering people. You can chaos 5 and 6. Let's go there. 2 square V1 is equal to what? V2. So V2 is equal to 4 times of what? V1. See? What I will now come and do? You have grabbed it now. The Rema. Now you are seeing. What do we do? Now you can see that we will happily get what we are looking for. How? I'll just carry it and put there. See life. You show them the way they left you and they are doing it by themselves. See life. Equal to 1 over 2. This. And V2 is now 4V1 all square minus V1 square. So changing this one is now equals to 1 over 2 real. So 16 V1 square. Man. Why do you like your me? You were not me. It's like you have in front. Be going. We will see in front. So, you know we have all the values already. This one is already, it's what? 45,000 equals to, this one at 1,000. So 500 now because of the over 2. 500. Then what do we have here now? Can we add it? So you don't know we can add it. Sorry for it. 15 V1 square. Me open the brackets. I won't open the brackets. Divide both sides by 500. It's the new people attitude. Engineers to like chaos. 90. 90 is equal to 15 V square. Divide both sides by 15. What? This V is V1. What's our V1 like this now? When you divide 90 by this one, 6, Abby. So, square root of 6. Press your calculator. What does it give us? 2.45. 2.45 meters per what? Second, sharp. You know the sweet thing about this is some students, when they finish, when they get, you know, after I suffer for long, you forget where you are going, what they say you do. You now go to double mark and go to the next question. What did they say you look for, please? This discharge, are we? Is that the discharge? We only needed this first to get the what? Discharge. What's the meaning of discharge? To get V2 is a problem. So, how do you get V2? In the research of it, do we really need to get V2? Because continuity makes us understand that the discharge at the V1 side is one, you understand? So whether we like it or not, any discharge you use is good. But you can still find V2. It's not good to lose things. You can still understand. You'll be a good mother. So, what are we saying? Even discharge, what's the discharge? Discharge is simply like your discharge, that's your volume flow rate. That's what it is. So that will be equal to what? AV. Do you get me? That's AV. So that's equal to what now? We have our V, we have our other things. So quickly now you have to find that area. Do you understand me now? You have to find that area now. You have to find that area now. Yes. You know the area, you know, if you are using A1, you have to use the 120 one that you used for the diameter. Or your fast, sharp. So that's what? 0 point. I'm using this one. That's 120. This was millimeter, Abi. Check, oh, millimeter. So meters. That's 0.12. Abi, I go divide by 2. 0.12 divided by 2, that's 0.06. That's radius. I like the radius way. By r squared.
You have 0.11.
That's what? 2.77 times, Abi 2 point something. Times 10 raised power of what? Minus 2. Abi? That's I'm saying 2.77 times 10 raised power of what? Minus 2. Abi? What will be the units? Volume flow rate is volume over time. Meter cube sharp. Now let us do Torricelli. 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 Is that, you know, by this? What am I looking for? Something I'm supposed to hide. She don't put this. Come and see it. Right, so I'm going to it. You know, yes. Where are we? Where are we? Torricelli's theorem. A large tank contains water to a height of 9 meters. A large tank contains water to a height of 9 meters. A small hole is made 2 meters above the base. See, a small hole is made 2 meters above the base. Look at something now. Let's say this is the tank. Let's say this is the tank. This is the height of the tank. The cover. Cover. Right. A large tank contains water to a height of what? That means from here to here is 9 meters. But where did they put the hole? Where did they put the hole? 2 meters above the base. That is, if the hole is here, that means from here to the floor is 2 meters. Are we together? What is it? You should determine the what? Speed. You should determine the speed of the efflux. The speed of the efflux. The efflux. I think they don't tell us what to take G and Z. So we should use what we like in G based on where you are. I mean now, can use what I like. It's mean I know the planet I'm operating from. Mars. Planets. Just try it. Just try it. Try it, please. What are we doing here, please? You agree with me that if this thing was filled to the water at this level, this something will start pouring out like this, through us. Are we together here? So yes, we want to calculate the speed with which the water is using to come outside. Oh, if I was the examiner, I will not change that question to projectile out. And as you're looking for who will do that. Yes. Yes, now it will make sense. You not tell the it's coming out now, horizontal projectile. At what point will the speed of the water of those converge? We'll just mix the dynamics with the projectile. Okay, let's go. Let's go. What is Pastor doing? Yes. Now let's go there. What are we supposed to do now to get the speed? What comes to your mind? To calculate the speed is that thing I will do. Thank you very much. Thank you very much. So solve. So solve. Square root 2 times 10 times. Waiting with the h for here. I knew that's where you miss it. No, see. The total, this thing, thank you, 7. 7. So don't go and use 2. I get me now. We don't use 2 because that thing, we are not using that h there. Does not stand for height. Do you know what it stands for? Depth. It stands for depth. For depth. 7. $11 points. That is the velocity of the air flux. They even has that thing. It's not me. Under the same question, determine the horizontal distance reached if the hole is 2 meters above the ground. It's not me. That means we are trying to check what is the distance from here to where this thing landed on the ground. That thing is called range. It's called what? Range. It's called range. What is connected to that? So yes, how do we get that range? Horizontal projectile. At J before, yes, now we're looking for the distance from here to here. That's projectile. Before we can get, there's nothing you can do. Nothing not to do. To get that range, you must go and first get time of flight. And the only way you can get time of flight is h equals to 1/2 GT squared. We know I've entered projectile style now. Is this square root 0.4? So now that I've gotten our what next? What next? The range now is horizontal distance, which is normal distance equals to velocity times time. Are you getting that now? So what does it give you? That I thought they say people are.
I thought they said you people are rotating now.
When?
9:50 for what time? 4 minutes. You cannot touch something in 4 minutes. Now it's talking. Stand for long. My leg hurts. So yes. Let me give you guys one question to attempt.
Just a normal basic question. Just very basic one. As in this.
All right. So yes, just yes. Are you on your pen? You gripped on your pen. You remember yesterday I was telling you something? That beyond this equation, there is also one more parameter that is there. The elevator head. Elevation head, I mean. The first one is the pressure head. Second one is the velocity head. The last one is the elevator head. I want to give you a question that has that elevator head. It's just rho GZ. If I rho GZ, rho GZ. Like it's time. It's time already. 2 minutes. After 150, we can maybe reach 100. Yes. At least they can pay you. So that is that. As you can see, we are working value. Replace the unit. Replace the unit. Always make sure you replace your unit. It's part of it. Part of it. Major part of it. Wait. Is that continue? So write this question down. Briefly discuss Navier-Stokes equation. Navier-Stokes. So, so which of the I think you are around one of the topics we did earlier on in our physics. One of the aspects of the physics. I don't know, I'm asking you. Is this the first session you are receiving? I'm sure. So this event, this is the first session. Welcome to Waves. Welcome to Waves. You met us at Waves. Sorry, timekeeper. Is it time for me to be able to go? Is it time for me to be able to take break? I won't take all my break. Yes, I won't take all everything. Look, take it. Yes. All right, so in 10 minutes time, I'll be back. 10 minutes break, please. Let's go back. 10 minutes. Okay. Okay. We are looking at a new session in physics. We are looking at a new session in physics now, and that is waves. That's waves. I'm not doing that. Yeah. So we're looking at wave now. We are going to be exploring all the properties of waves, ranging from characteristics and the types. We'll look at the wave motion, try to analyze every single thing. So please make sure you do well to ask questions. If there's anything you do not understand, feel free to ask questions. Feel free to ask questions, inquire. If there's anything you don't understand. So let me check. What is this? Waves. Waves now. No, like, what's wave? Okay, so we are now in module 16. All right. All right. So good. When we hear the word waves, what should come to your mind is disturbance. What comes to your mind is what? Disturbance. A disturbance. So a wave is literally a disturbance that transfers energy without causing a net displacement in the what? Medium of propagation. So the medium that is propagating the wave do not experience a net displacement or a change in position of the particle or the constituent that makes up the medium. Do you understand? The reason that's going on is that what? Is that the disturbance travels independently of the what? Of the particles that makes up the medium. Are you getting that gist? All right, very good. So write it down there. The wave is any disturbance. The wave is any disturbance. I get it? It's any disturbance that travels and transfers energy without causing a net displacement. Without causing a net displacement. Without causing a net displacement in the constituents of the medium. In the constituents of the medium. Are we together here? So when you hear that thing wave, what does wave carry? Let me ask you. Energy, thank you very much. So it is carrying energy and transferring energy. But is the material medium actually moving? No. A good example is the water ripples, right? You will see, when you throw a stone into the river, you will see that there will be formation of ripples. Those ripples, when they are traveling alongside with energy.
They are transmitting energy, but the water particles themselves are not, the makeup or concept of that particle are not going to be displacing away from their original X position. They only experience a Y displacement of which they will return back. Do you get what I'm saying now? They only experience a Y displacement of which they will return back. You can see, I think we said this already. A wave is a what? Disturbance. You pay attention, you find out that wave will be your best topic. It's a disturbance that transfers what? You need to understand those things, those highlights. From one point to another without the what? Permanent transfer of what? Matter. That permanent transfer of matter is the same thing as saying without a complete displacement. There is no actual displacement in the component of the matter that is propagating the medium. Do you get the gist? Now, examples include sound. As I'm talking to you, can you hear me? Do you know why you can hear me? Very good. Because as what I'm saying is coming out, it is causing a vibration on the air molecules. And that vibration is being transmitted to your ears, and they sensitize the auditory nerve, and your auditory nerve will now send the signal to your brain and interpret the sound. That means if there were no air available here, there would be nothing to help to propagate the sound. Now, when I use the word propagate to transmit the sound, I get what I'm saying now. It's very simple. Seismic wave. Do you know what I mean? Seismic wave? This is an earthquake wave. When earthquake comes to start, you're going to hear that. You understand? It is a wave. And also, light is also a wave. But that's the most controversial particle in the whole of physics. Light. And I know why they say God is light. Light has not been fully understood till today. Yes. But let's not go there. Now, wave theory forms the foundation of what? Acoustics. Should I make you understand something? Do you know that if there was no air to propagate sound, if an explosion happened, you will not notice it. You will hear it. It's because of the fact that there is air that you are able to hear those sounds. You have what we call acoustic sensation, the ability to hear energy. Yeah? Yeah, that's the meaning of acoustic. I get me now? The ability to hear energy. You can hear energy. You can hear energy. You can see energy. You can feel energy. Your senses are constantly exposed to different types of energy. Can you hear me? Now, we have communications and we have quantum physics. You see that quantum physics is going to be happening in the final day of this event. That is the modern physics, the beauty in physics. That is the last meat inside the food. Always the sweetest. Now, next slide, please. Now, a wave possesses what? Look at we are talking about characteristics of a wave. You enter into the exam hall, an A-level exam, they ask you, state the characteristics of waves. As you are seeing states and you are seeing wave, you are not even supposed to continue. You are writing things. What are the characteristics of waves? That same thing as saying properties of a wave, makeup of a wave, the things inside the wave. I get what I'm saying now. Every wave must possess amplitude. Except you are not a wave. If you are a wave, you must possess amplitude. What is amplitude? Now, amplitude simply means when the wave is traveling, the maximum vertical displacement that you see is the amplitude. See, as I'm going like this, guys, if I draw it for you now, see what you're going to be seeing. You see something like this. You see something like this. Are you seeing it? Let me imagine that my this thing started from here. You see this thing here? It got to this side, it stopped, it needs to come up. It now look as if you are a French student, it now look as if there's one support and resistance also happening here. The thing does not want to break from here. I get what I'm saying now. That thing there is amplitude. The highest vertical displacement. The highest what? So that's what we call amplitude. So amplitude is here. Let me tell you what some people used to do. If exam, this one, the only one here, this one is your benefit. If they ask an exam, locate this point. Maybe they call you a point P, the next one, identify this point. 90% of Nigerian students will call it crest. Sorry, they'll call it amplitude. This point is not amplitude. This is the point. Amplitude is not a point. Amplitude is a distance. Do you understand what I'm saying? Amplitude is a distance, not a point. I get what I'm saying now. This line is what we call my principal axis. What do I call it? My principal axis. So it's as good as saying amplitude is the what? Is the distance from my principal axis to the what? What's the real name of this place? The crest. Do you understand what I'm saying now? So it is the distance between my principal axis or my equilibrium axis. I'm giving you names to the top place. Hope you know that this event happening up, they're also happening down. If you look at it, there's also this downward maximum something going on here also, Abby. That one too is called amplitude. It's also called what? So we have the upper amplitude, lower amplitude. That's why when you want to identify amplitude, you can't use one number to write amplitude. You use range, and the range must be, we call it uniform range. Then I are saying -2 to +2. I get me now. That -2 to +2 means that this was a graph like this. They're trying to tell us that this wave is traveling, in terms of its vertical displacement, is traveling between +2 in the positive y and what? And what? Oh. And what? And what? And -2 in the what? And -2 in the negative y. I will not get used to stress. Now, look at this. You're moving like this, you're moving like this, you're moving. This is the wave. Now, we want to be picking out all those things that they are calling characteristics of a wave. Here now, I've shown you the amplitude that we favor. What did they say amplitude is? Amplitude is what? Maximum displacement in the vertical direction, Abi? Good. Now, how about wavelengths? People, I can bet you 95% of people don't understand what wavelength is. Many a times, if they tell them define wavelength, they used to write rubbish. Things that cannot make them give them full mark in an A-level exam. They might give them the mark in O-level. But in A-level, they won't tolerate it. Define wavelength, somebody will now say wavelength is the distance between two adjacent crests. It's not a line. Two successive crests, that's the one you like. It's still not complete, it's still not valid enough. Because let me tell you what a wavelength is. A wavelength is actually, imagine this point here. I see this point here. Where is the next point that is identical to this point? The next adjacent replica of this point in this up place. Is it this one? No. This one is coming out. Maybe we are looking at the one going up like this. Where is the next one that is going up exactly in this place? Where is it? It's not here. Abi, that means from here to here is also a wavelength. From here to here, truly, is also a wavelength. From this place, where is the next identical place of that is like this? It's not here. Open it, not here. This one here, Abi, it's another wavelength. This down one, throws. This is the next identical part like that, Abi, is another wavelength. So when we want to define wavelengths, it just goes beyond saying identical and successive. Let me just read this thing, please. Because I see you vexing for me today. Okay. Sorry. Yes. Yes. Yes.
Wavelength. So, what does that mean? Now, I have my hand for full gestures. Yes. Wavelength now, it is what? It is the distance between two identical points. Two adjacent identical points, or say two successive identical points in a wave. So it can be the distance between a crest and a crest, the distance between a node and a node. I get what I'm saying? The distance between a throw and a throw. It must be identical points. I get what I'm saying? It must be identical points. That's how this thing works. So I now understand that you now know the meaning of a wavelength. See, don't worry like all this of they will draw a wave for them. When they draw a wave for them, they will now ask them, what's the wavelength? See that it's something. They'll draw a wavelength. They will now ask them, what's the wavelength? They will now be thinking the wavelength is the length of the wave, the full length of the wave. No, let me show you something. Okay, let me put it like this. Between this wave and this wave, which of the wave is longer? Between this wave A and wave B, just try. Which of the wave is longer? Based on what you see. A and B, or which one has the higher wavelength? Thank you, B. Because this one wavelength is, if I want to read it from here to here, true or false? Why this one wavelength? You can see it from here to here. You can see it, Abi. So that's the goal. That's the idea. That's the idea. So I'm sure you are clear with wavelengths now. Now, the next thing we want to look at there is the what? Frequency. When you hear the word frequency, we're talking about the time taken for what? One complete cycle or one complete rev. Anyone else call it. I get it now. That's frequency. You can't look at the wave and see frequency because frequency here is an event. I get what I'm saying now. But you can count the cycles. Look at something. From here to here is the full cycle. Because if you check it, if I cover this place like this, it will form a full cycle. I get what I'm saying now. And a full cycle is how many degrees? Like if I should do full cycle, it gives us something like 180. Right? That line that you see in between. Don't worry, get it. But you understand what I mean by frequency, I mean? Good. Then when you now talk about period is the time taken for, do you understand? The time taken for a number of oscillations to be complete. That's period. But when we want to standardize it, we say for one complete oscillation. Then we now say speed. We know what speed is. Thank you. Speed is simply the distance over time. Good. Now, energy carried by a wave depends strongly on its what? Amplitude. Do you even know this statement? When you say energy carried by a wave depends strongly on its amplitude, it means that if you see a wave that has a high amount of energy, it is because it has large amplitude. So by mere looking, I know that this wave has more energy it's transmitting than this wave. But if this wave was like this,
Then this one has more energy than this. Their what? Their amplitude is what mirrors their energy. Their amplitude is what does what? Mirrors their energy. Simple. So wave motions can occur in where and where? Solid, liquid, gases, and vacuum, depending on the type of what? Wave. Electromagnetic waves, they do not need a material medium. So that those ones can be propagated in the what? The vacuum. Next slide. Now, waves can be generally classified into two. We can classify waves into two. What are those two? Thank you. We have the mechanical wave and we have the what? Electromagnetic wave. When we hear the word mechanical wave, it's simple. Exam tells you, define mechanical wave. You say the words are no more than 5. These are waves that what? Require material medium. You get full mark. Don't worry, don't try to fill the pages. Just write that and you get full mark. A mechanical wave is a wave that requires a material medium for its rate in propagation. But what about electromagnetic wave? Those ones, they what? They can propagate through a vacuum. That means they do not necessarily need a material medium for their what? Propagation. That's it. So I believe now the concept of mechanical wave and electromagnetic wave is a done deal for you now. Now I believe you now know what the wavelength really is. It's not just crest to crest and through to through. It's about successive identical adjacent points. Very simple. Now, matter waves describe quantum particle. Wave may also be progressive or stationary. And let me explain what those things mean. When they say wave can be progressive or stationary, most waves, you see them, they actually travel, they move. But there are some waves that we refer to as standing waves. Like all those ones that are happening in a pipe, in a string, all those standing waves, stationary waves. We'll explore them, you will see, you understand. Next. Now, mechanical wave relies on interaction between particle and medium. That's why we said they need a material medium because there's an interaction that's going to exist between the two. Example includes what? Sound wave, seismic wave, and wave on a string. Now, their speed depends on what? Elasticity and what? Density of the medium. No that one. But I'm going to bring formulas that will depict it. Now, this is what we're saying. How elastic? You know what the meaning of elasticity? Good. In fact, when they measure elasticity, don't think of stretch. Stretch is the correct example, but it's not the situation. Elasticity is about being able to regain your original dimensions, your original shape after deformation. Do you understand? After what? Deformation. A deformation has occurred. You now want to what? Regain your original dimension. That's why you say that you're elastic. Do you get it? Now, when you say density, can you imagine this air? Imagine the air was very dense, very compact. Will you be able to run fast inside? The less dense the medium, the faster or the easier it's going to run. And even air the resistance to some of our motion. You get it? So it is logical to know that these two things will be able to influence speed of the wave. Now, next slide. Electromagnetic wave consists of
oscillating electric and magnetic field. And you know the thing that is not mentioned in this place? Maybe they tell you to talk about electromagnetic wave. You have to state it that words. That the way the electric and magnetic field propagate, they propagate such that they are 90 degrees to each other. They are waiting. 90 electromagnetic wave contains electric wave and magnetic wave separately that are traveling 90 degrees to themselves. Let me give you a pictorial view. This red marker, I'll use it for magnetic waves. This blue marker, I'll use it for mechanical, sorry, for the electrical wave. You know, electromagnetic wave contains electric wave and magnetic. Electric, magnetic. Now, see something. Imagine now, I want to draw a wave traveling in this direction. Let me imagine how to draw a wave traveling in this direction. Let's imagine the electric wave I want to draw this. This is what it looks like. Jesus. We have this. It's not clear enough. It's not visible enough. This is much better. Good. That will show you the electric wave. Now, what did I tell you? I tell you the magnetic wave will travel. They will travel so that they are at 90 degrees. This wave that is traveling like this, the other one will be traveling. That means if this wave is traveling like this, so like this, the other wave will be traveling like this. I get it now, 90 degrees. So that means this other wave here, I want to draw it now. I want to draw something a bit visible. That's something like this. Don't get it twisted. Wait. The visuals will show something like this. You get it? If you notice, this thing looks like 90 here. I mean, and it continues like that too. You can see like 90 to themselves at different points. They exist as if it is 90 to themselves. Just because don't mind my drawing. What I'm trying to tell you that what? See this beginning, the way this one is going vertically, but this one is going horizontally. Do you get what I'm trying to say? That's the propagation of movement. So good. They are traveling through vacuums at 3 times 10 to the power of 8 meters per second, which is the speed of light. Which is the speed of light. Examples include radio wave, visible light, X-rays. Are we there now? Examples include what? Radio wave, visible light, and X-rays. But if you also mention all of them, that's your words. Your revox, I mean, it's your M. RM evox, radio wave, microwave, visible light. All right. Next slide. Okay, this is it. Now we are looking at something transverse and longitudinal wave. Another way to classify wave. The first one we're classifying based on material medium, maybe. This one we're classifying based on how it is propagated. And based on how they are propagated, we'll be having longitudinal wave and transverse waves. Longitudinal wave and transverse wave. What's the meaning of transverse wave? Particles oscillation is what? Perpendicular to wave propagation. That means, when you say wave propagation, that means the thing that produces the sound. How are you traveling relative to that? For instance, let's imagine with a guitar here, there's strings on it. And I do like this. How do I play the guitar? I transfer the string away. Right? Now, I now want to study how did the wave travel. Did it travel perpendicular to how I transversed it, or exactly that direction? Is that same thing with even your water wave? Do you know what I'm saying? So transverse waves are waves that travel how? Perpendicular to the direction of the wave source. But what about the longitudinal wave? This one travel parallel. Let me tell you something. Example of parallel wave is sound wave when you're talking. Because sound wave depends on the air that surrounds you. So look at something. Imagine this is a speaker. I'm just gonna know. When this thing start propagating, what really happens is that the air closer to it, we start doing what? Compressing. But the compress, after a period of time, what's happening? The last start loosening up. I get what I'm saying now. And that thing can continue like that. Repeated compression, retraction. I say that. So these regions where there is higher density due to compactness is called rarefaction. But this region where they are spread out, the region where they are spread out are called what? See what I'm saying? Compressions. So the regions where they are spread out, what do you call it? Rarefactions. Very simple. Very, very simple. This is something I'm very. Now, that's for transverse and longitudinal wave. And then example include light wave and waves on a string. That's for transverse wave. Because a wave on a string, you propagate it this way. Why does it travel? Perpendicular. Yes. And propagate like this, you travel like this. That is transverse. Another example is what? Your light waves. I get what I'm saying. Light waves. Very good. Next. Okay, this is the next. Particle oscillation is perpendicular to wave propagation. Particle oscillation is parallel to wave propagation. Now, compression and reactions regions are formed. Then sound wave in air and longitudinal. I just restated. Next, amplitude. We are looking at maximum displacement from equilibrium. Wavelength, we are looking at distance between successive crests. Frequency, number of oscillations per second. Period, time for one oscillation. Now, it's not deeper than that. It's not deeper than that. All those kinds of things we call them wave parameters. You must have certain parameters with you, even though you are doing something serious in waves. Your amplitude must be on ground sharp. Long ruler must be on ground, not massive ruler. Long ruler must be on ground. How together? Now,
A wavelength is the distance between successive crests. I think I told you this one already. Now, back to frequency, we talked about that. Period, we talked about that. Next, wave speed depends on what? Medium and what? Restoring force. Wave speed depends on the medium and the what? Restoring force. The what? The fundamental relation is B equals to what? F lambda. B equals to what? F lambda. That's the fundamental representation of the wave speed. Is that clear? Now, increasing frequency causes a decrease in what? A decrease in wave length. Do you understand that statement? Because we know that from here, I can bring out the fact that F is equal to V over lambda, and that shows that inversely proportional. The higher the frequency, the lower the what? Wavelength. That's it. That's it. Next. Phase and phase difference. When we hear the word phase, phase is just a characteristic point along the wave motion. A characteristic point across the wave motion. Phase describes the position of the particle in its oscillatory cycle. That's why you begin to ask yourself, am I in phase with you? Should we be out of phase? Those kind of questions. They're trying to check their own movement if they're still on point. Phase difference determines whether waves interfere constructively or destructively. Do you see that? Phase difference determines whether waves interfere what? Constructively or destructively. Now we explain that to you. It's very simple. Very simple. Now, see what we mean by this. If you have one wave here, so like this. About one wave like that. You have one wave like that. Let's imagine you have another wave in this place like this. What can you say about this wave A and B? They look very identical. True. They literally have the same number of wavelengths. But this way I'm going to, I want to look at the face. What we mean by face is, if it is any point at all along the line of the wave. So if I draw a line from here to here, bisecting two waves, we want to check if the two waves are in phase. So this is what I need to do. When I do these three things, I'll check where you met you. I get what I'm saying. This means that the two waves are in phase. But if you saw a wave like this and you like this, automatically, these guys here, are they in phase? So good. I have gotten the gist. Now, see something. We are coming from the same place, just different points. You mean we are going to go and meet today? I get what I'm saying. If I was going to meet today,
Let me put it here. But let me imagine forgetting it direct. Do you think it's exactly the same number of, if you look at number of peaks you have, do you think it's exactly the same direction? It will be higher. One, two, three, four, five. 1, 2, 3. 1, 2, 3. 1, 2. Well, what you can see is that you can see the angle phase having good. Then how do you know the phase difference? By knowing the number of waves that are there. The number of waves that are tempting. For instance, this is it. Today, you know, watch this movement and identify the talks with us. And find out the person. You get it? So that's the case. That's the case. We had how many wave peaks? 1, 2, 3, 4, 5, 6. But now, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. See, the number of waves that are extra is what you call your. It's what will determine if you're doing constructive or destructive interference. Just have it in mind. And that's in mind. So that's what we call phase difference. Phase difference. That's it. Alright. So your phase difference, if your phase difference is an even number, maybe the wave that was supposed to come to this place, it went like this. Also, if you keep like this, I can see from this one that there is one full wavelength here. Can you see it? So that means how many wavelengths make up this path difference? 2 wavelengths. So 1 wavelength. Do you see that now? I was saying that how to do this in markets. So that's it. What's the next thing? The general harmonic wave equation it's good. It describes the displacement of the particle as a function of what? Position and time. But it forms the basis of advanced wave analysis. Very simple. So what it's trying to say is that those few parts it has in that slide, we should not remove it. Are we together now? All right. All right. Energy in wave. Wave transport energy and what? Momentum. Mechanical energy oscillates between kinetic and potential forms. Intensity is proportional to amplitude squared. You need to know all those things. Proportional to amplitude squared. Yes. Now let's now have a look at some other things. It means that for that phase angle material, if you want to give you a material, I will give you dash as it, and I come and show you 2 component waves and ask you which one of them is. Maybe I just ask you which one of them is constructive, or which of them behave like a destructive.
cannot compute. No need.
So that's that. When two or more waves overlay, now this principle of superposition. Now, when two or more waves overlap, resulting in the resulting displacement equals what or the grind sum of the individual displacements. What does that mean? What it means is that if I have a wave traveling like this, imagine you have a wave like this, and you are adding it to the wave like this. And listen to this now. The first thing you have to say is, are they in peace? Yes. If this place came up, this place came up. Down, down, up. This is also yes. In peace. But the question of the is this. What kind of interference is present in? Is it constructive or destructive one? It's a constructive interference. It's a constructive interference. How? Before you can have a constructive interference, it means that these stocks must follow themselves perfectly well in this pattern, and they must be in phase. This side came down, you can see it the same time this side came down. This one came up, the same time it came up. Do you get what I'm saying now? Please, oh, please. So this one will give me constructive. Okay, but what about if this was what we had a wave like this? And I add it to wave like this. This one was destructive. But by the time you overlap, what you form will be something like this. Right? Which looks like that's cancelled out the waves. Exactly. Look like the wave was on. But it's not cancelling out. It's just a beautiful ending. It's a beautiful ending. This one is going to form something like this. See now, what it means is the amplitude in the result is higher than what both of them be. That's why it is called constructive interference. Are we good? Alright. Alright. Now, it said, when two or more waves overlap, the resultant displacement equals to what? Yes. This principle leads to interference phenomenon. I guess what I'm saying. So you can be there in any of these kind of cases. All right. So good.
A constructive interference occurs when waves meet in phase. So we both have to meet in phase. Whether you are meeting in phase to form, whether you are meeting in phase to form a what? To form a constructive interference, but you are moving in phase to form a destructive interference. Shall move in phase. Alright. Resultant amplitude does what? Increase. Did we do it there? Yes. And laser operation is key. This is key. That's new technology. Alright. Occurs now, destructive occurs when wave meet out of phase. Now no longer in phase. This is not what we agreed. Then not registry. Resultant amplitude decrease becomes 0. Application into nursing, application include noise cancellation technology. You see that now? You see that now? You see it? I'm already having that syndrome. So that's it for that. Next. What's the standing wave? In standing wave, good. Standing wave results from the what? Superposition of what? Identical waves traveling in opposite direction. So I have a wave, identical, same amplitude, same wavelength, same all those things. But this one is moving like this, and I have another wave moving like this. I get what I'm saying? This one is moving like this. I get what I'm saying now. You can see they're moving in opposite direction, Abby. This one, they call it what? Standing waves. Standing waves. So they can ask you, what leads to the formation of standing wave? Standing waves are formed when what? When two identical waves. And when they use the word identical waves, amplitude are the same, wavelengths are identical, Abby, and traveling opposite directly to themselves, Abby. When they collide with themselves, they will now form what we call a standing wave. Do you see that now? So superpositioning of identical wave traveling in opposite direction is what we call it. Very simple. And whenever that thing happens, we will have the formation of nodes and what? Antinode. Imagine these two things. See them. Imagine these two things. Just meet and they click. Let me do it properly. It's supposed to be like this. It's supposed to be like this. Yeah, If they should collide, this place will now be the one covering this place. Before you know, the wave that will form the look like this. I think that now, this is literally a what? It's literally your normal standing wave. All this space are what? Nodes. Region of minimum displacement. While all the sides are your what? Antinodes. Very good. Standing waves are essential in musical instruments. Very key. Okay. Now let's now click into resonance. I've not yet talked about the characteristics of a wave. Oh, you know. Have I mentioned anything about characteristics of waves to you? Not. Resonance occurs when driving frequency. Resonance occurs when driving what? Frequencies. Equal natural frequencies. This statement here, resonance occurs when driving frequencies equal natural frequency. Now, if I place an object, let me just imagine maybe an object hung from a height. I place the object near another body. I get you now. Identical to him, even in terms of height. Once that guy is one of them is oscillating, it will induce oscillation in the other body at the natural frequency of that body. You get it now? That's it. Next. Next. So we're having that. Example includes bridges, buildings, and turning fork. So an oscillation in one body can trigger another body to start vibrating at frequencies that are what? That are their natural frequencies. That is what's going on in waves. Very, very simple. We have not mentioned anything calculation yet. So application of wave, medical application of ultrasound, wireless communication, earthquake studies, that's both your P and S, seismic waves. Then remote sensing. Okay. So yes. The next thing now that we want to do is we want to look at the characteristics of a wave. The characteristics of a wave. Once we have done with the characteristics of a wave, we will now enter the next topic, which is electromagnetic wave. Wave introduction is not getting deep. Summary, volume 1. So the finish with that one. Let me finish it. The remaining thing that is not inside there. So yes, watch. Characteristics now the question is, so the question is what? The question is, what are the properties of a wave? What are the characteristics of a wave? Okay, it's there already. Oh, that's that for my one. Now, we have reflection. We have what? Refraction. Thank you. Polarization. Interference. I get what I'm saying now. These things are properties of waves. Other properties of waves there, we have what? Diffraction. So good. These are the main properties of waves. These are the main properties of wave. These are the main properties of wave. All right. So yes, what is reflection? Thank you very much. This one is the bouncing off of radiations that are incident upon a smooth metal surface. So imagine we have a surface like this, and the wave came like this, in straight line, to strike the surface. Waves have the ability to get reflected. And they get reflected following certain rules that we will still discuss. Okay.
So that's for wave reflection. Reflection. So the angle of that incidence is equal to the angle of what? Reflection. Now, another thing we'll talk about is refraction. I think we'll talk about the topic. Refraction. Refraction is the bending. This one is bending away. This one is the bending of light wave as they cross the boundary of two mediums with different densities. Is that density difference that causes that? That's part where they tell you, dip your spoon inside water and look at the glass spoon. It looks like your spoon has broken. That mirage is because of this situation, this scenario. Yes. What are we talking about? I'm saying that if this is the medium boundary and this one is a dense one or dense, less dense, and this one is denser. I get what I'm saying now. We know that when a wave is coming like this, normally, if this medium is not there, if it's just a single medium, this wave will travel like this. Two of us. Now, how will you want to get back for a service like that? Question is, whenever you pass this is normal. The first thing you have to do is to understand that moving from a less dense region to a denser region actually brings your chances like this. When light waves are moving from dense to less dense, they are faster in less dense. When they enter dense regions, they are very slow. They are very slow. Some of them say the image won't show. So just have it at the back of mind that particular stuff. So listen up. So by the time this radiation has entered here, I get it now, because it entered a denser medium, it's going to bring it closer to itself. It's going to bring the radiation closer to the normal. This is normal. It's going to bring it closer to the normal. Do you understand? That's it. This thing is called reflection. Bending away of light rays and cross what? The borders and boundaries of mediums with different densities. Okay, that's it for that. How about polarization? You know, some waves travel here. One is traveling like this. A wave can travel like this. And now again, it doesn't zone, can travel like this. Another one can travel like this in the Z direction. That is a thoughtless person. When they are going to say it is fashion, they have used your way and break the rule of waves. What makes it drawback? So that's that for that one. So polarization is the ability of scattered waves, I get now, to be propagated along a single plane. Along a single what? Plane. That's what we are doing there. So for polarization, you come to polarizer or you test to see and come to two. Okay. Matter wave describes quantum physics. No one is true. What is it? Interference, yes. Yes, the interference here now. Polarization. Polarization, I said, is when you are causing waves to come out in a single way. Given that there are many ways, you can untangle it easily. But what I said about interference now was this. This thing and this thing is interference. Even what was supposed to happen on Monday, it's supposed to be an interference. Do you get it now? So that's how the life is. So let's go into interference. Interference occurs how? When what? Okay. So, as if I want to just appeal and ever carry a fan or carry something and say, if it interferes, but in wave motion, interference is beyond that. Interference is beyond that. And what interference? When two waves set there, when two waves, just like superposition, so that in superposition you have to become the sound. When two waves, I get you now, healthy and what? Of good behavior was coming from you, we need to check the behavior of the animal you want to see. It's nonsense. So we'll check all those things. So, and then the money will be paid once confirmed. Now, back to what we're doing. Diffraction is the bending of waves around obstacles. Bending waves around obstacles. We are not still quantification of waves. So yes, you can move the slide. Move the slide, keep moving. Okay, that's all. Let's do the slide, the last one. Go back on this. So we have finished the slide. Okay. Now I'm giving you classification and characteristics of the wave patterns. So you should be able to read at any time. All right. That's the first part of waves. What did we talk about in that one? Can you give me some? Just what you remember is that you know you held tight. Okay. Alright. You want to ask a question? Use your mic. Yes, you know, it's on. Gentlemen and ladies. So we are done with the first part of it. Want to move into electromagnetic wave. Electromagnetic wave. What is an electromagnetic spectrum? And frequency. The thing I want you to remember is this. Now, an electromagnetic wave, a spectrum, is the spectrum of electromagnetic wave consisting of what? All radiation arranged in order of their what? Frequency or wavelength. Now, the electromagnetic spectrum consists of all four electromagnetic radiations arranged according to order of wave. So it means the highest is still what? Radio wave. The depth of wave length. What is the next one? It is microwave. Good. The next one, infrared. The next one, visible light. The next one, why not in the mic? Yes. This one, it's usually not to the mic. It's working. Visible light. What's it? That's the. Ultra. So we have X-rays. Oh God, thank you. Not those men talking like this. So that means love. But our next one, gamma ray. People call it gamma radiation. Gamma ray. That's it. Now, they will ask you in an exam, which one of these radiations has the highest frequency? Which one has the highest wavelength? If you don't know, no problem. But you want to try, which one has the highest wavelength? No, it's the first one, radio wave. Let me tell you how you remember. Have you ever wondered how something can be happening in something FM, in radio FM, far away, but you are receiving the signal in another place? All those kind of things utilizes radio wave. Radio wave prioritizes wavelength and frequency. We need longer wavelength because of bandwidth and transmission signal. Since I'm talking like I'm working telecom. Do you know what I'm saying? But that's what I'm saying. Yes. So that's the thing. So anytime in the example, why do I tell you this thing? Anytime in the example, and your mind just, once you see that kind of question, your head just clicks and remember that, oh, I remember it is wavelength that it decreases downwards.
because the number one there has the highest wavelength and it will be decreasing. So if they tell you arrange all of them in order of decreasing wavelength, decreasing, that means you start from the highest to lowest. Who is the highest? Radio wave, followed by who? 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 So that is it. But when they want to ask you in terms of frequency, remember, wavelength and frequency are two inverse properties. I get me now. So any parameter that has a high wavelength must automatically have a low frequency. You can't have the two of them opposite. Like you can't have them in quantity. If one is high, automatically the other one is low because they're inversely related. So automatically, who do you think here has the highest frequency? Thank you very much. Who will have the lowest frequency? Why? Because radio wave has the highest what? Wavelength, photon. Now, that is one thing about science. You see, you enter the exam hall, they will tell you define a spectrum. Define what? When they tell you define a spectrum, some people, the name, that in the spectrum, just scatters the whole of them around the exam. They won't understand that spectrum simply means an organized arrangement of radiations. So when they now put electromagnetic spectrum, we are saying is the organized arrangement of electromagnetic waves in order of what? Increasing wavelength or frequencies. I get what I'm saying now. Organization, no, that's the spectrum. Now, we've already said it before, that's why this is not going to be long. Electromagnetic wave, did they need a material medium or did they not need a material medium? Electromagnetic, they don't. Mechanical need. Electromagnetic don't need. They can propagate anywhere. Do you understand what I'm saying now? They can travel in a vacuum. In a vacuum only. Okay. Next slide. Now, all electromagnetic waves travel at the speed of what? Light. Now, let me ask you a question. Where among these radiations, where is the light that we used to see road? I've given you a clue. See, check that statement that said, where is the light that we used to see road? Thank you. Visible light. Is visible light is called visible light because the wavelength and frequency of visible light falls under the band that is optically friendly. I get it now. Our eyes can absorb those radiations, frequency and wavelength, and interpret it. Do you know that there's colors your eyes can't even absorb? Have you woken up in the morning when white light just shines inside your eye? You don't know that you face the sun. And just open your eyes and lose guard, or you don't know the paper. Your dream was too dark that you don't know that there's light. Only to open your eye, don't open it carelessly, one. You know, you close your eye back. When you close your eyes, you'll be seeing green. There's this green thing you'll be seeing. I don't know what to call them, I don't know their name. But you'll be seeing this green yellow thing. But mostly green yellow, or even when you look at the sun outside, you see the green yellow. That's because green is not a friendly color to the eye. Now, somebody said that God did it that way because He doesn't want the human eye to be harvesting the energy in the color green. That energy is meant for plants. No. I don't think it makes sense. Do you understand? But it makes sense now. I was the one, it was one guy that was catching me that day. I just reasoned it. It would be like that too. So let's go. Now, spectrum. Spectrum, now we've said, is the arrangement of radiations in an organized array of frequencies or wavelength. So all electromagnetic waves travel at the speed of light. All of them, they travel with the speed of light. Now let me tell you something. This visible light, hope you know that they have their own spectrum too. The spectrum of visible light. We call it Roy wave. I follow you. Do you know the meaning of Roy wave? Do you know it? Do you know the meaning of Roy wave? Royal purple, orange, yellow. Then this one is Amarita green. Right? What's this G? Green. I'm not sure Amarita green. This one is what? Means I know the best. This one will be like Gombe pepper red. You know, it's ladies that make color a problem for people. You can no longer buy gifts for them again. But they'll tell you it's color 24 you want. Since when? Burnt brown. So, you see the way this microwave infrared is following themselves before visible light. That means the first radiation in visible light is the color what? Red. So, radio wave, microwave, infrared rays. If you want to mention it in detail, who is the next first member of the visible light in that arrangement? Red, then orange, then yellow, then green, blue. Then this one is what says? Indigo. Then what? Violet. Now, that means, who is the last frequency in the visible band region? Violet. That is why there is a wave theory catastrophe that happened one time. They called it the ultraviolet catastrophe, because that had to do with something about despite the fact that violet is the highest in the band, something we're expecting something in terms of intensity, and it did not happen. But I'm not going into that gist now because it's a gist part of the pepper soup for topic 30. It's like topic somewhere around topic 30 to 36. So let's move. Radio wave. Now, radio wave are the longest words, wavelength, and lowest words. Does it make sense to you already? On your mic, please let me join ours. It's on. Check. I can talk. Very good, very good. What is it? That's the one, three. Do it. Now, radio wave are the longest wavelength and the lowest frequency region of the spectrum. Now, what's their application? In doing waiting, does it make sense? Yes. We've mentioned it earlier. In fact, what we mentioned was the next one, which is what? Radio communication. I get what I'm saying now. And they also use it in navigation system. You know that in my navigation system? For example, flight navigation, airline. Plane 101, Eric, do not land. A plane is coming, approaching, blah, 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 blah. No, they will not land. That's also radio wave communication. Do you understand? Okay, next slide. Okay, microwave. Used in satellite communication, radio system, and the most important that me alive in microwave oven. Even if you don't remember, you should remember that microwave are used in microwave oven for cooking food. I get what I'm saying now. So you're not even scared. That's something that they're using for satellite communication. It's what they're using to warm your food. Now, I don't know, it's only God that has to keep us. It's what I said to do wireless networking technology. Very interesting. Next slide. Next. Even that infrared rays that we just passed, you know that thing has more application than that. Look at something. Who is the nearest radiation to visible light? Infrared. It means that infrared has the tendency to make images visible too. It's not just naturally visible everywhere, but it can make images visible. Soldiers use infrared light to fight in darkness. Hope you know. They will wear their infrared glass and they'll be seeing your image as green. I get you now. Sometimes it will be reading your temperature changes. They do it to be reading your temperature change. I know they do those things. So you see, infrared have more brutal application than that's in the root. And that's in the root. Later, in your free time, go and read about the radon girls and you will learn many things about errors that have been made in the past. So, visible light is the only portion detectable by the human eyes. Ranges from red to violet with decreasing wavelength. Obviously, it has to be with decreasing wavelength because we are continuing with the trend. You get? Now, ultraviolet radiation. This is one of the most impacting radiations. It has both debilitating effects, good effects. I don't just know where I will put this radiation. If you'd ask me today now, Henry, your decision is final. If you say you don't want radiation, you would ban it in the O8. I don't know if I will ban this thing, despite the damages. So it is used in what? In what again? Fluorescence. In what? Forensic science. But excessive exposure can damage biological tissue. You know, some people that prepare slides like this, like me and some of my team, we don't like using harsh words. For me, I can use harsh words. It can just lead to cancer. Let's just write it. You understand? That damage to tissue is cancer they're talking about. Do you understand? Because those things are mutagenic. They are oncogenic. Do you know what it means for something to be oncogenic? It has the ability to stimulate proto-oncogene pathways that can trigger second messenger systems responsible for mutations. Let's not go there. Let's come back. Now that's that one. Next slide. X-ray. So X-rays are highly penetrating radiations. When they say penetrating, they have the ability to pass through your soft tissues. I get you now? So they are highly penetrating radiations used in medicine and crystallography. This crystallography, who was the scientist that brought about the study of crystallography? Braggs. Who finished the work on crystallography, did all the derivation? Me, Henry. For that time, my other name was Mosley. So Henry Mosley. I get me now? Henry Mosley. Now I'm not a practice, so when I achieve all those things, I have to change my name to restart and do another one. Do you get? So, move on. So yes, gamma ray. It is the highest energy electromagnetic radiation. Do you know? Let me tell you something. Maybe we said as you go down, frequency is increasing, Abi. So that means gamma rays have the highest frequency but lowest wavelength. Let me show you something. E is equals to HF. No be so. Telling you that the higher the frequency, the higher the what? Energy. So any radiation that has high frequency usually have high energy. You don't want to play with gamma rays. You don't just want to. So applications include cancer treatment. Now let me tell you something. People that know the damage of gamma ray, that even have cancer, when they tell them that okay, these are available options, some of them need to pick the fates. No, there's no need. Because you're coming out, even if you survive the cancer, you can come out and the new developments might be something you can't live with. Do you understand now? So it is the other fact that they use the word cancer treatment is a debilitating approach. It's an approach that is not, it has high risk. Even upon successful treatment, exposure to radiations is not something too good. You understand what I'm saying? All right, the next one, I think that's below. All right. Electromagnetic spectrum comparison. So frequencies increases from where? Radio wave to gamma ray. While wavelength decreases, wavelength decreases for the highest is that this one. Photon energy increases with what? Frequency. So if they say photon energy, I said that already, increases with frequency. Who has the highest photon energy among all the members of the electromagnetic spectrum? That will move. Gamma rays, because they have the highest frequency. So therefore we have the highest.
and what they call it? Energy. Reflection of electromagnetic waves. Reflection occurs when waves encounter a boundary and return into the original medium. Yes. You get that now? You get that now? Next, dispersion. Different wavelengths travel at a different speed in a medium, causing what? Separation of colors. I believe you've done this experiment in secondary school. You've not done it. I saw that moment. Did they show me glass prism? So, when you pass certain white light through a glass prism, when you pass through that glass prism, I get it now. When it is emerging, it emerges in its components. It will obey the Roy beef. The Roy what? Beef. Say beef. This is the mind beef. Don't sound something. Say that again. You're trying to teach beef. Next one, please. Next one. Before you leave the list. Scattering. Good. It explains the blue color of the sky and red appearance of the sunset. How do they mean? In the first lecture, I was mentioning something about aurora borealis and aurora borealis. How many of you have thought of it? Where did they get the word aura from? This is what they have aura. Go and check the picture of an borealis. See, that's where one of the major scattering happens at the geographical pole with the intention of protecting us. God really. I was going to take a minute to worship Jesus. Yes. See, he created physics not only for us to study but to protect. Because in the Earth's region, we are covered and surrounded by magnetic fields responsible for deflecting and scattering harmful incident radiations coming from the sun. It will not deflect them to the poles where there are heavy gases responsible to desensitize the charges and scatter them to make them even appear beautiful. So something that's supposed to damage us now become a center of tourism. See the beauty in God's doing. See, I'm talking like I said, like me too. I've gone to Australia to go and check Borealis. Good. So that's cool. The red appearance of something and all is because of scattering too. Next slide. Polarization. Only transverse waves can be polarized. Let me see. If you have sense, you will know what that means. You know that the need of polarization is because of how you are traveling. Somebody who is traveling in a straight line. If I clean it, see the people, very obedient people. This is a kind of relation of longitudinal one. See them, very good. They are traveling in a straight line. Those kind of people, do we need to shout, line up in a straight line again? No. Transverse waves, they are not traveling in a straight line. They are wave itself. Some of them, why some are going like this? Some can be going like this. But polarization is just like, see, God. You must understand the name is marker. Imagine there is a small door here. This is a small door. Right? You agree with me that this door, there's only one way this marker must orient itself that will make it pass through this door. True of us. Good. If this marker is traveling like this, can he ever pass through this door? No. But you agree with that if they are like this now, they are traveling like this. You agree with that this is how waves travel. Many different waves traveling. And so by the time they get to this place, only those waves that were in position, in other words, pass through. That's what we call plane polarization. So it's me that will decide how I want them polarized. If I want them to be oriented like this when they pass through, at the end of the day, I will have only radiations and waves that are in this straight pattern. If I wanted it the other way, I will turn this and polarizer like this so that only those that are in this plane will come out. So polarization has to do with a technique of intentionally engineering a means to orient your way to do what? Propagate in a given direction. I don't want waves scattering up and down. I want the wave propagated in this given direction. That is plain polarization. So that's why I say you cannot polarize a longitudinal wave. You only polarize a transverse wave. Are you with me? Are you with me? Speak to me. Are you with me? I can't hear you. Thank you. Next slide. Optical fibers. Some people, the only fiber they know is food. The fiber is high food. Fiber makes no sense. Optical fiber. Optical fiber use total internal reflection. Pause. You see, this is where magnificent students used to shop. They will want to read this place. Optical fibers use total internal reflection to transmit information over long distance. After this, we'll go to the next slide. Somebody who does not know the meaning of total internal reflection, you are going to the next slide. What are you doing in the next slide? Do you know the meaning of total internal reflection? Now, look at it. It's not hard. It's simple. This is about to tell you the concept that can come out to your exam this year. Very possible. You can enter and just realize number 2. God works in different ways. Don't worry. Don't read those. You open the one who is one out to get. But watch. We have this. We have this medium. Let's imagine we have this medium. This total internal reflection only happens when the incident ray is coming. Are you following me? When the incident ray is coming from denser medium to a less dense medium. Do you get what I'm saying? Between glass and air, which one is a denser medium? Right? Very good. Now, see something. So let's imagine that here is glass, and down here is what? It's air. Are you following what I'm saying? Now, this place, let us imagine that the radiation came from here, struck this normal. You know, we have a normal like this, have we? Good. You know, when you are moving from a dense medium to a less dense medium, by the time you are crossing the boundary, what happens? Because you are moving to a less dense medium, you become freer to move, right? The guy, instead of moving closer to the normal, that is moving closer, instead of, you know, this is the normal axis of continuation. Instead of moving closer to the normal, you will not be moving away from the normal. I think that with the second side, the more you increase the angle of incidence, how do we increase the angle of incidence? By opening it further. So instead of this line, I increase it like this. What do you think will be happening to this one? This one too will be going up and down. So there will not be a point in time that a particular incident angle, there will be a particular incident angle that will make the, you know, this one across the refracted ray, that will make the ray lie down exactly on the boundary. Lie down exactly on the boundary. The name of that incident angle that did that special wonders, that made all the refracted ray now lie down on the boundary. They call that one what? Critical angle. What do they call it? Critical angle. Now, it means if I open this thing small again, above the critical angle, what will happen to this one here? This one will no longer be here at all. It will not enter inside here. Good. So that means any angle, the angle of incidence greater than the critical angle will lead to total internal what? Reflection. That means there will be no refraction again. Rather, this thing now will be a full, do you see that now? Reflection. So when does total internal reflection happen? When the angle of incidence is now greater than the what? Critical angle. But what's the second condition? The propagation of the radiation must move from a denser medium
to a less dense medium. Very simple. Who press next? Please let me take the previous. Optical fibers use this principle to now transmit information over a long distance. Do you understand? So next. Yes. Waveguides. Waveguides direct electromagnetic energy efficiently in the microwave engineering. We don't want multiple dispersal of our electromagnetic energy. So we create a confinement that protect that wave and contain the wave so that it can be available for stipulated, I must blow that grammar, stipulated judicious use. Next slide. Radar system. You see, radar system, as I saw radar, I feel not good. Radar system uses reflected radio waves for detection, navigation, and speed measurement. Do you know what? I will complete this write-up. Detection of walls. Have you never heard when all these white countries are saying you cannot cross their radar? But once you cross their radar, they will detect you. It gets me wondering if we have radar. There is no issue. In normal countries, they have these radar systems that are made up of radio waves. So that any single object, whether you're in bed, I get it now, whether you're in bed, once you can't see those radiations. So you don't know they are there. So for the moment you just touch one, it has sent them signal by reflection to their office that so radiation is so region just got contact with something and they have started checking that premise. See high level tech. But in our own, let's go. Next, satellite communication. Communication satellites rely on signals across continents and oceans. Next, mobile communication. Cellular networks rely on what? Microwave and radio wave transmission. Yes. It's very normal. That's a lot of communication we're talking about. Next. I can't hear you. You went twice. Wi-Fi and wireless network. There's something interesting I want you guys to know. And some of you here believe also, it's even you out. Do you believe that microwave is dangerous to our health? Exposure to the microwave. But you know many people that believe that it's dangerous. I mean, so I believe. I'm a believer in that ideology. But this is the part of it that I understand that looks like hypocrisy. Except it's ignorance. You believe that microwave your food in the microwave kitchen can cause cancer. But you are not worried about the fact that it's still microwave frequency that operates as network and wireless connection in your phone. You will leave the Wi-Fi on one pocket and put the other one that is the receiving hotspot, the other pocket. You go on behind to see what you are hearing. So, all those things have an application. So they are used for networking system, wireless connections. Next one, laser technology. Laser stands for light amplification by stimulated emission of radiation. We are going to treat it in applied physics. We fire out electrons to excite them so that when they fall, I get it now, they will fall and release photon radiation that we now see as light, targeted light, high energized light. Next. So that is that we have this microwave equivalent of laser technology. Next. That one now is microwave amplification.
So medical imaging, we have these medical images, your X-ray, MRI, PET scan, they all rely on electromagnetic principle. Next, you don't want to start doing all of these, they are imaging something on magnetic resonance imaging, the X-ray, you know your normal X-ray now, all of the imaging, we use to see what goes on inside the person. We can't always go invest, you understand? Alright, so remote sensing. Satellite collect environmental data using multiple regions of the spectrum. You see that? That was common sense. Next, astronomical application. Astronomers observe celestial objects across. Very good. So I don't think now the issue. Next, electromagnetic compatibility. This one now we are studying interference between electronic systems and method of mitigation. So we want to learn, these electromagnetic waves, are they compatible with these other radiations? Are they compatible with these kind of chemicals? If they aren't, what are our contingency plans or what are our mitigating plans to prevent re-incidents of such occurrence? Next. Federal radiation. These are emerging technology in applications, in imaging and communication with an advanced. It's part of the nano and tech that is presently ongoing. Yes. Better material, still artificial intelligence. I think this lecture has already based on all the things that are already going to apply. Better that's artificially engineered materials capable of visually demonstrating behaviors that are peculiar to electromagnetic waves. Okay. Yes. Photonic crystals. Structures designed to control the movement of photons. So that photons don't just disperse them and start coming discussing damages between them. It's now more controlled and streamlined. Yes. Quantum communication, using quantum state protocols for secure information transfer. So people don't just bowl into your privacy, your files and documents. Yes, next. The president. Just continue. Okay. Can go back 2 steps back. So quantum cryptography provides theoretical communication channels using quantum mechanics. And that quantum mechanics is the thing that we'll be addressing soon. Okay, next. Future technology, advanced communication system and quantum times, and then the original lesson technologies. So that promising that times have been to us, we are waiting to see it, quantum damage. Alright. We just don't know what we must do one day we will dig it because of the plans ahead. Next slide. So this summary next. That's what I mean. So we have come to the end of wave and electromagnetic waves. We've come to the end of waves and electromagnetic waves. So this one now is for what? At all. All right. So we are going to go into sound wave. But before then, I want to ask some questions. So therefore, just briefly summarize anything you learned from the class, this topic of waves down to electromagnetic waves. Just say anything, right? As much as possible. True. That's the key word. True. Thank you very much. True. True. Thank you very much. This is this thing I said. Why is it not person? You pay attention to everything is about 6 marks like this. So, okay, simple. Yes. True. Yes. Very good. True. You have tried. You have tried. It means you have learned. Thank you very much. I appreciate it. Let me now move to sound waves. Have you ever imagined to? You just learned the grammar. Question number 1. Define sound. Did that mean you know that there are many common things you don't know how to write? Or you don't learn that they define signs. All of you know that you define sound. I know you know it. I know you know what sound is, but can you remember what it is? Now, when you tell you to define something as a wave, let your definition hold true that it is a wave. I get it now. Let your definition hold true that it is a wave. I'm not going right now. So it is not okay enough for you to just say, okay, and now it's not sound wave. Sound, I don't know sound, don't worry, I don't know how to put it. That's why you need to know how to put your mark. You understand? So you need to know what you're doing. Now, sound is what? A wave. What kind of wave is sound? Longitudinal wave, right? So it is a longitudinal wave responsible for sensation of the hearing. To put it in better terminologies, we can use the word responsible for auditory sensation. Responsible for auditory sensation. Do you get it now? So it is even important for you to even know that sound is an energy. The kind of energy we hear is sound. The kind of energy we see is light. Everything around us is energy, including what we feel. I get what I'm saying. Everything is energy. Everything is energy. Very good.
Slide, please, slide. Slide, man. So, the first question that I'm going to ask you, what reason do you think, go back to the place, that's where I want to ask. What's so interesting about this image that you use for the front? Let's video or sound. Guess. It's something very intellectual, very intellectual. Serious. Yes, see it very look deep. It was the wood. Okay, the thing is ordinary. Now, I'm telling you, what is this image that makes it a perfect image for us to place as a front cover for the sound picture? And I find it in 10 seconds. It's there, it's there, that thing is there. That thing is. Should I tell you this? Should I tell you this? There's no reason at all. It's for me putting it there. Next slide. Next slide. No reason. You're overthinking. That's my point. Now, characteristics of sound. Without the definition of sound. So please, hope you're writing a definition of sound. Sound is what? You can put that in like, sound is what? Your mic, sound. You someone can tell us what sound is. I feel like you're going to yeah. Sound. Whatever. Thank you very much. It's responsible for auditory sensation. Auditory sensation. And when you say auditory sensation, in human language, we call it for hearing. General. So, what are the characteristics of sound? First thing first, we know that sound is the mathematical representation of a longitudinal wave. We've appreciated that in the previous lecture. That sound wave is a longitudinal wave. Put together here. And then, another important thing about sound, in terms of characteristics, is that sound must have intensity. It must have what? Intensity. Another name for sound intensity is called what? No? Another name for intensity is called loudness. Sound has loudness. And loudness is relative. Loudness is what? It's relative. Do you know what I mean by relative? What might be loud to you might not be loud to me. Because everybody has different threshold of hearing. Do you know what I'm saying? So that's what characteristic of sound. Another characteristic of sound is quality of sound. Quality of sound, which is regulated by superposition. Sometimes good sound can be coming out, but because of noise around, the superimpose the sound and reduce the quality of the sound. Then we have interference of sound waves via beats. We can form either constructive interference or destructive interference. Join choir in the church, you know here now. Don't know anything about sound. That is not the last few words in beats. See, it is not here. It's the difference between one level in pitch and another level in pitch. It's not drum beat we're talking about here. It's not drum beat. Now, out of all these things, it's important for you to streamline the concept to this, of characteristics to this. Because out of all these characteristics, we have only 3 main characteristics of sound. What are 3 main characteristics of sound? We have pitch, we have quality, and we have intensity. I get it now. This quality is also called timbre. Intensity is also called loudness. Pitch is also called pitch. But each of these characteristics, they depend on certain things. For instance,
pitch depends on frequency. It depends on what? Frequency. The more the frequency, the more the pitch. Quality in timber depends on something we call overtone. Intensity depends on something we call what? Threshold. Observe. Yes. Before I move further, there are certain things about sound in snow. Was I heard the word sonic? Sonic. Sonic. Right? This word means something related to sound. And then we have this like this sonic stuff. We have something that are infra sonic, something that are ultra sonic, we have that are suprasonic, subsonic. How do you get it now? When you are talking about supersonic and subsonic, those ones are talking about the speed of sound. What do I call it? Speed of sound. If an object or a wave is moving with a speed greater than the speed of sound, which is about 343, that wave is going to be said to be suprasonic. When a wave moving with a speed less than the speed of sound, we consider it was sonic. But when we have those moving with a frequency greater than the normal frequency of sound or hearing, we call them words ultrasonic, very high frequencies. But very low frequencies like your seismic wave is your ultra infrasonic. Next slide is unit of chapter. We talk about Doppler effect, shockwave, and sonic boom, the application of sonar, ultrasound, and medical imaging. Next. Okay. Sound can travel through any kind of matter, but not through a vacuum. The speed of sound is different in different materials. In general, it is slowest in gases, but fastest in what? In solids. I get it now. It's the fastest in solids. This speed depends somewhat on temperature, specifically for gas. Very, very important to note this. Very important to note this. One next. Conceptual example. Adapt lightning strength. A rule of thumb that tells us how close lightning has struck is 1 mile for every 5 seconds. But it's not that ahead. Explain why these words works. Nothing that the speed of light is so high, blah, 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 blah. This person is trying to do poetry, sciences. But eventually, just trying to make us understand how lightning moves with speed of sound. You understand? Move with speed of sound. Eventually, you have the air between speed of sound and speed of light. Which one is faster? Speed of light. And why do you see the lights or hear the sound? You understand? Good. Let's go. So you can see our rule of recorded sound. Loudness related to the intensity of the sound. Pitch related to what? Frequency. We said that earlier, right? Frequency. Audio range about 20 to 20 hertz. Upper limit decreases with age. Ultrasound. You can see that we have examples. Let's go.
focusing with sound waves, other autofocusing cameras that are digital directing pulse. So basically, there are some cameras that focus utilizing sound waves, vision of sound waves. That prevent vibration and compression. Next. So mathematical representation of longitudinal wave. And longitudinal wave are often called pressure wave. The displacement 90 degrees out of the phase is the pressure. That pressure is as a result of the fact that there are some places, what controls the whole spread of the wave is pressure. Any region where you are seeing high compressions, that region has higher what? Pressure with high density. Do you understand? But the regions in the other place are lesser. Do you understand? Okay. Now, move to the next thing. By considering a small cylinder within the fluid, we see that the change in pressure is given by B. We observe this, right? Okay. Next slide, please. So, mathematical representation of longitudinal wave. If the displacement is sinusoidal, we have this. Okay. Now, when you hear the word sinusoidal, I'm saying that it is a sine wave. It will move like this in the graph. Like this. Right there now. So that's what we are saying. That if the displacement is sinusoidal, we have this. So that's what the function will be. So that's a lot of intensity of sound. The intensity of sound is the energy transported by unit time across a given area. The human ears can detect sound with an intensity of very good, as low as that. You see, you don't come with anything higher than that. Then perceived loudness, however, it is not proportional to the intensity. Yes. The intensity of a wave is the energy. Is the energy transported by unit time across a unit area. When you hear the word intensity of wave looks like power of the wave. It's literally the power of the wave because energy per unit time is power. So we're checking out how we are spreading the energy of that wave across board. So you have something like this. Imagine the speaker is here now. And this thing is releasing sound like this. As the wave travel pattern, their spread becomes even greater. Their spread becomes even greater. And that's the thing. Their spread becomes great. That's the issue. So yes, these regions where there are more lines, that's the region where you see the intensity is greater. Are we together here now? So it is simply energy flowing in this place per unit time. So it means that I'm saying that power over time is equal to what? Sorry, energy over time is equal to power, which is equal to what we are doing. So in this case now we are saying all over area. So this is
over area, that's pull over area, power over area. But the earth is a spherical medium, the spherical place. So that means that we are going to be propagating the sound spherical, which is the free propagation. All right, so we are having intensity to be equal to power over area, which is what per meter square. So that is it. And this 1 per meter square is called what? Okay, the human ears can detect sound with an intensity as low as what? 10 to the power minus 12 Weber per meter square, and as high as 1. Perceived loudness, however, is not proportional to intensity. Next to so the loudness of a sound is much more closely related to the logarithm of the intensity. Sound level is measured in decibels. So we have sound intensity and we have sound intensity level. If we are talking about sound intensity, that's what we just did. That was denoted as what? I. But we are talking about sound intensity level. That is the loudness at a particular distance from the sound source. That one, we represent it as a logarithm of the intensity. That's why you see it is like B is equal to 10 log, open bracket, I over I. I think column I naught over I. I naught is not taken to be the threshold frequency of hearing. It is a constant. It's the threshold of hearing. 1.0 times 10 raised to the power of minus 12. We have the threshold of hearing, threshold, all right. Next example, sound intensity on the street. At a busy street corner, the sound level is 75 decibels. What they use and measure sound intensity? Sound intensity. That one is what? That one is what? No. What we use in measuring it? We've arranged it many times. Sound intensity on streets. At a busy street corner, what is the best to use? Airport, I mean. That's the best to use on street. Now, that's because it saves every other person of the pollution of your phone noise. Because it's only you that might be enjoying that music. You are not interested, and we might not be interested. Even if you like the song, you might just be in the worst mood. So sincerely, when it was getting to something now, up there in your ears. What is the intensity of sound there? No, But you work day zero. They work with day zero. This standard physics units. Which one? Okay, the dB is the unit of sound intensity level. We call it decibel. DGAO, not decibel. Decibel. Okay, listen up. Let me bring out some calculations. Okay. Ready? I'm waiting for her to solve finish. You're not getting it solved. Look at chronologically. I watch. All right. So we're having B to no sharp. B log. Okay. So we said at a busy street corner, the sound level is 75. What is the intensity of sound there? Sound level. Hey. Oh, this one. Okay, call on the call for you. What's the words? I didn't hear the numbers. What are the numbers? Okay, good. Okay. You still be working on that. Something on the street. Next slide. I'm going to do something else. Why explain the concept? Next. Oh. Okay. So, intensity of sound and intensity sound level. What is the difference? What is between intensity of sound and intensity of sound level? All right. All right. So, decibel increase in sound level, increase the decibels, which is the doubling intensity, is a very small change in loudness. Open ear areas, the intensity of sound diminishes because distance. However, in a closed spaces, this is complicated manifestations. It small travels through air. You got it? Okay. So, an increase in sound level of 3 decibel, which is the doubling intensity, is very small change in loudness. In open areas, we've spoken about this. However, in enclosed spaces, this is complicated manipulation. And if sound travels through air, the dynamic frequencies get really absorbed. Okay? When the 3 and increase the sound level of 3 decibel is the doubling intensity. This is the same item. But for me, it's not. Nice. It's not a testimony. So, okay. However, in enclosed space, this is complicated at all. Next slide. Good. The sound level measured 30 meters from a jet plane is 140 decibels. What is the sound level at 300 meters? Yeah. Okay. I think the solution will be the next slide. Next. It's just questions. Yes. But have you understood the concepts? The calculation is not going to be a problem again. So that's good. Yeah. Yes. Sources of sound, vibrating strings, and air color. So look at this musical instrument produce sounds in various ways. One vibrating strings, Maybe they for the phone, vibrating everywhere. All those things are making growth. So, so, so we want to go into a part of this sound wave where we're treating standing wave. I want to sleep for 50 hours. And I finished this thing, I was sleeping for 80 hours. I can't feel my eye. Yes. All right. Now, there are two major sound systems that we treat in physics. And those are organized sound. Those are strings and pipes. Strings and pipes. So, when we hear those strings, what we're talking about, I'm talking about lyrics. The string was not a length, right? And the way you plug it and make you see it very yes. But at the same time, this plugging that brings out only one stop like this is called your fundamental. The fundamental note, which is the first note. And that first one has an expression. Yeah. Second, this one is the second harmonic, we call it the first overtone. So you have first harmonic, zero overtone, and the second harmonic, the first overtone, then that's Okay. So sound dry. But I really stream the air quality. That was very starting. So this guy didn't produce sound in various ways, like with strings, breathing in the brain, activity in the house, or wood shapes, by the different objects. The revolution is started by object of striking, boundary or blowing, the revolution that translates to them, and then to is. I'm supposed to be reading. I left the reading for you. So, I'm more interested in the air calling and the strings. I see that they highlighted them back. Move to next. Yes. Sources of sound. You get sound from notes. Where do you see notes? What are notes? So when I don't know them. And those ones. So yeah, if this is fundamental roots, I will call it first harmonic and zero bottom. This next one, what do you think we call it? This is what do you think we call it? Second harmonic and first bottom. Any power to make pass. This one only tone harmonic. This one is what? Third harmonic or what? Second over. That okay. Drink for 15 minutes. All right, now I can that one I'll be doing something. Yeah. So, if I want, okay, I have explained this. I have not. There's a calculation I want to do. And next slide, I can see. First fundamental note. This is the first overtone of second harmonic. Third, second harmonic. Second overtone of so on the first harmonic, our length is equal to 1 over 2 lambda. On the second one, it becomes L equals to lambda. On the third one, it becomes L equals to over 2 lambda. I bring So, take it back. So let us make this guy subject formula. Wavelength. Wavelength is now equals to 2L. But here, and this one, so this one, number 3 equals to 12 over 3. Sharp. So from here, we'll recall that velocity is equal to what? Velocity is equal to distance, wavelength lambda f. So let's bring in on the lambda for each. This one now is 2L. So V is equal to what? 2LF. Understand? This one I'm still catching. Drink. So we know that this side we're going to substitute. Make f equals to b over 2l. For the fundamental, I will call it f1. Apply this on the zero. F is equal to v over lambda and v over and 2 over l. How to get the frequency of each? So normally, you know the formula. Velocity is equal to lambda wavelength. And that means frequency is solve the formula. You start getting my answers. Your point. I did it. I did it. Frequency goes to v over lambda. Or lambda is 2l.
Because so that so listen up. So I have just there. So let me know that all of the associated frequencies. There are these frequencies that people as well. There are these frequencies. So that you F1, F2, and so the two people then I have the frequency about viewing and code. But I'm thinking you as well. Let me give you an example. If this is the reference, this how many times answers does this one have? The value is how many times? This is 2, 1, 2. Because of so, I don't do any processes. Let me just do what I'm going to do.
Continue. I'm active. Active. Waiting for my break. My 7 minute break is not waiting for. Like this. Yes. I want that. So the principle is simple. The monic number is the coefficient of that stuff. Right? Period over 2L, then we have 2V over 2L, 3V over 2L. This is going to be 4V over. You get it? So frequency equals to 4V over 2 lengths. 4V over 2 lengths. Yes. From this, you can draw out a conclusion that shows that F2 is equal to 2 times F naught or 2 times F1. Next. Is it ready? The highest key on the piano corresponds to a frequency about 150 times that, 150 times that of the lowest key. If the strings for the highest note is 5 centimeters long, how long would the strings for the lowest note have to be if it had the same mass per unit length and was under the same condition? Next slide.
Anytime you have break, say to the markers.
Break, okay. True.
Make it count to rest of it.
Yes. Come on. I don't take. So yeah, I'm going to be looking at the sound wave from vibrating strings needs to be amplified in order to be a practical balance. This is not an acoustical issue. We're using the soundboard, the voice, written resonance chamber. Sound can also be amplified in a true can. Really should create sound through sound waves column of energy. So there are two kinds of pipes. One the open pipe, the closed pipe. Open pipe, this is resting in the hands, both at the open. Now, what we is exactly what we have been doing. Strings, bow, crispy, as a model, slightly different, or you see. Yes. Back. This is what your closed pipe is. This one is open, you can see both ends. That was closed. So let's work on this one first. So remove, and then we have the antennas. The antennas are regions of maximum displacement, while the nodes are regions of minimum displacement. Okay. So there's a lot of work as well. One, yes, two, three, 24, second week, first, bottom. V is equals to, and that F is equals to V lambda. Lambda.
want to change the mic. Yes. So F2 to the material. Next slide. All right. So we're done with this. Next slide. For these ones, they only use odd number of harmonic. First harmonic, third harmonic, fifth harmonic. It continues in that way. So right here. We're gonna go. Go. Tiens. Tiens, ça. Vas-y. Don't worry. Almost. Time break, guys. Good. Okay. So I'm going to be drawing to illustrate some things for the meantime. So for this, no problem now. So this, the third harmonic. The third harmonic under this aspect is referred to as the first overtone. The first overtone. Why this one is the second overtone, regardless of the fact that it's the fifth harmonic. Yes. So from there now we can now expand on that. We have this other one. This example stops at drawing the second overtone. So we're going to get a third overtone. It's going to look more like this. Yes. So this one here gives you a third overtone, and it's the length of column will be equal to 7V all over lambda. 7V small, yes. Okay. You can have this seventh one. And the seventh one here will become 7 all over 4 lambda. So we call that F is equals to V all over wavelength. And wavelength from this place, consider wavelength is equals to 4L over 7. So substituting it, you have F equals to 7V over 4L. So that's what it is. Understand? That's what it is. So, sorry for the obstruction earlier on. So that's what it is. This same scenario is what you use to get further derivations. Your F, you have F1, F3, F5, F7, F9. You only have odd number harmonics from your closed pipes. Odd number harmonics only. So this one here is like the fundamental. This one becomes your first overtone, second overtone, third overtone, and fourth overtone. You get that now? And why is that? Because the first one is where you have the V all over 4L. V all over 4L. And if you check every other one, they're just having this number multiplied by V over 4L. So we're having 3 into brackets V all over 4L. Next one is just 5 into brackets V all over 4L. This scenario continues that way. And then we'll get to that point where you can now say V all over 4L, comma, 3. Instead of writing V over 4L, you know that this V over 4L is referred to as F naught. So we can call it 3 F naught, 5 F naught, 6 F naught. Sorry, 7 F naught. All that matters is just for you to remember your notes fundamental. You get it now.
So from here, we can now dive into other advanced aspects. Is that clear? We can now dive into other advanced aspects. So yes, from this, you can further deduce some of the things that happen in beats and when you run calculating octave beats in music. So a beat is simply the difference between two identical notes in successive octaves. In successive octaves. That's what it is. Do you understand? In successive octave. If it's the difference between two identical notes, notes that are the same, in successive octave. That's it. So that's what it is. So that's the last part of sound waves. We dive into light wave. We dive into light wave. Right. No. Optics. 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 The distraction is much. So optics, in optics we're studying light. We're studying light properties ranging from light propagation to reflection, refraction, and optical instruments. In this one here, we're going to talk about aberrations. This one here, we'll talk about aberrations. Aberrations. We talk about mirror and lenses. Aberration, mirrors, and lenses. Okay, so we start from the first part. Light. What is light? Light is the form of sensation that we see. The sensation that we see. The photo sensation that we see, we process through our optic nerves and get interpreted in the CNS for response purposes. Very important. So you know that there are many ways you can apply the concept of light travels and all those things. One of the ways is in what? Is in eclipse. Eclipse and shadow formation. Eclipse and shadow formation. What causes shadows? Obstruction to light. Whenever something is along the path of light propagation, it casts shadows. The object shadow gets casted on a screen. And the shadows are usually divided into two categories. You have the region of the umbra and the region of the penumbra. So we have the umbra regions and we have the penumbra region. This one is the region of complete darkness.
Why this region here are not as dark as the umbra? That's because of little light that forms the margin, of the eclipse. So we also have different kind of eclipse. We have the annular eclipse, right? We have the solar eclipse when it is the sun, when the obstruction is between the moon and the sun, right? Good. So it can also be as a result of perturbation, where different planets come in line with themselves along their orbital, thereby disrupting the free transmission of light from the sun to the planets. Do you get that now? So that's part of that. Then we have reflection. What do you mean by reflection? We're talking about bending away of light rays after their incident on the surface. That thing is controlled by a law, which we call the law of reflection. It says that what? It says that what? The angle of incidence is equal to the angle of what? Reflection. Incidence angle is equal to the angle of reflection. Are we together? So, yeah, should give me 2 minutes. I'm supposed to have time now, like 5 minutes, right? Yeah. Okay. So, angle of incidence goes to angle of refraction. You can also obtain what we call a glance angle. This is the angle from here. It's called the angle of the glance. It's called the angle of glance. It's called the angle of glance. So the angle of glance usually is equal to 2 times the incident angle upon rotation. Rotation is, imagine the surface that was like this. You bend it this way so that it now aligns with the incident angle. I get what I'm saying now. What that usually forms is to create a scenario where this guy will become 2 times what the incidence was. I get what I'm saying. So that's what the case is. That's what the case is. Right. Let me consider that 5 minutes has reached. I'm sorry, where did I stop? What's the last thing I said? Where did I stop? Yeah? Okay. So that's it when it rotates. Good. So we'll go to combination of mirrors. Once you understood glasses, you will not have problem with combination of mirrors. So imagine we have one mirror here intersect with another mirror here. So if a ray of light travels from here and strikes on this side, it's going to cause a deflection to this side following the law of reflection. At angle of incidence should be equal to angle of reflection. And obviously, when this reflected ray incident here, it becomes an incident ray 2. And it also do the same thing. Yeah. So this tells how many images that we should be expecting from here. So we are expecting the formation of how many images? 2 images. 2 images. So the angle of inclination of the mirrors usually can also affect the number of images that will be formed. So we have that formula as number of images formed equals to what? 360 over theta minus 1. Do you get that now? 360 minus theta. 360 over theta minus 1. So what about when we have composite system like your kaleidoscope? Like your kaleidoscope. You have one mirror here. You have another mirror here. This is an application of mirror. When a radiation comes from here, strike this mirror, parallel rays of light, it gets deflected. It reflects upwards. Let's place this mirror properly, and something like this. It get reflected upwards, such that this mirror tends to also reflect them in this direction. Reflect them in this direction. Yeah? So the kaleidoscope is used in military services to view images at heights that are far apart from where the observers are. So an observer can be here. This is where he places his eyes. But he's literally seeing events going on here. Because images here are being transmitted through light into this place to sensitize him. Do you get now? So that. Yes. So we have that. We also have its application in binoculars. Binoculars is just extension of lenses such that we can have a greater reach of view to see images from a large or far distance. No. Binocular is a different application as well. While the kaleidoscope is trying to manipulate light, a binocular is trying to make far sight possible, not hide boundaries, not hide defect. It's just trying to make you see images that are fine. It brings them closer due to arrangement of lenses. Organize those lenses in an organized pattern where the position of the lenses tends to make it possible to bring fine image closer to the focus of the second power lens. The kaleidoscope is different. Imagine this is a mountain here. You would have to actually mount the kaleidoscope. You understand? So that's it. All right. Now that we have done that, we want to look at mirrors. We want to look at mirrors. Mirrors can be classified as what? Plane mirrors, and we also have what? Curved mirrors. These curved mirrors, you can call them spherical mirrors. Plano convex, plano concave, they are not mirrors, they are lenses. So, on this video here, some of the major characteristics of the plane mirror is that what? Is that they form all kinds of images. They form real images. What else do they form? They form lateral inversion. You can't just say inverted. You get it? Because they don't turn the image upside down. The kind of inversion they do is lateral inversion. It's only spherical mirrors that will invert the image. Normal plane mirrors do not turn images upside down. They only work to prevent, they only induce lateral inversion. Now, what is lateral inversion? Your right hand side starts looking like your left hand side starts looking like your right on the mirror. It doesn't turn you upside down. That's the characteristics of curved mirrors. Right here, another thing about them is that the image distance is also equal to the what? The object distance is also equal to the image distance. Same thing with the height. The image height, HO, object height, is also equal to the image height. And that tells you that for plane mirror, there is no magnification. For the plane mirrors. The plane mirrors, now we have two categories of plane mirrors. We have those that are tinted, double tinted, we have those that are single tinted, but just that the back mirror is transparent. Right? So those kind of mirrors, where the back mirrors is not like a lens mirror, like a half lens mirrors. Those ones will form virtual image. You can't capture them on screen. But the normal plane mirror give you a real image. You can capture it on the screen. Literally, people snap the photo of plane mirrors and snap. You understand? An example of a virtual image is what you saw in Spider-Man. You come from home and be out from home. Yes. The image of, yes, it's formed behind the mirror. They are formed behind the mirror. That's not the intersection. Not the intersection we're doing here. Some of them can go behind. If you have another something here, it can intersect, and you're receiving image signals from there. So that's that for that. So from there, you can also explore curved mirrors or spherical mirrors. So the thing about curved mirrors is that we get it for spherical mirror by cutting the mirror at desired sizes. But regardless the size you cut, it still maintains the focus, like the center of that spherical complete ball, where you cut it from, still maintains to remain the focus of the already extracted curved mirror. You get now? And so we have two main types of curved mirrors. We have the concave and the convex. Concave. So how do you identify the concave mirror? What kind of mirror is this? This is a curved mirror now. We've got a spherical mirror. The origin are from spherical mirrors. But what kind of mirror is this one? This is a concave mirror because the convex side has been coated. So the observation site is from the inward curve. You are not looking at the coating. This place that I did like this means that there is no mirror from here. The mirror is only available here. So even if I did not draw this diagram and I drew it like this, if it was here I coated, this place means it's from here that you have the mirror surface. This place you don't see anything. This place is what coated. So since the place I can see something from is bulged out, it becomes convex mirror. Remember the difference between mirror and lens. The difference between mirror and lenses. Do you get that? So that's what it's been, that's what we've been doing for a while. So yes, after this, yes,
The concept from the, they have like the same pattern.
no,
Okay,
yes. They are characterizing in how they form their images, the nature of the images formed. And that's dependent on where you're placing your object to form your image. If you are placing your object at the focus, the properties of the image you get will be different. But when you're talking about general characteristics, right? The general characteristics, very general characteristics is what I've already said about identifying the region quoted and the site of view, place of view. Then, if you place this mirror like this, it has a focus here. That's another focus here. The focus behind someone is a what? That one is virtual focus. Any image formed at this side behind mirror is usually virtual. So we have parallel plane of lights traveling, strike this mirror. The mirror has been engineered in such a way that all of them will come and converge at the focus, except the mirror has an aberration. And different types of aberration. We just talk about the common aberrations, common aberration, talk about these aberrations. That's what we're looking at now. So this is what that's going to do. But if it's to be this mirror, parallels of light strike it. These ones still have their focus. It's just that these rays will get reflected outward in such a way that when you continue the line inward, they will all pass through the focus at the virtual side. They will all intersect at the focus at the virtual side. This intersection, that means that the mirror can focus. If all the rays are intersecting at one point, it tells us that this point where they intersected is the focus. But when it is focusing behind the mirror, it means that it will more likely be forming virtual images. Yes, you cannot capture them on the screen. Do you get that? So that's that. So we're always looking at these mirrors and we're putting objects at different positions and we'll be using certain analysis to determine where the images will be formed. Do you get that now? Using that to determine where images will be formed. So yes. So yes, I'm going to wipe off the board now. So we're looking at formation of images. Formation of images. So just imagine we have this image here. It's a concave mirror. This is the focus. There's also a place we call the center of curvature, which is twice the focal length, which gives you the radius of the curvature. Let's say it's here, we call it C. We also have the same thing on this side, to prime them for their virtual. You want to ask a question? So let's start from imagining what happens when the object is placed behind the curvature. The first radiation travels straight, parallel to the axis. When it wants to diverge and converge, it will converge through the focus. The second one will pass straight through the focus, get to the screen, and this place where it intersects is where the image will be formed. Right? So that's how we form images. But I didn't draw this thing to scale. I didn't draw this to scale. But if you draw to scale, you find out that some of the characters can see that this image is a real image because it's formed in front of the mirror. And that camera is inverted, but you can see it's formed below the principal axis. Right? And that thing you can see is the reference positioning. It's formed between C and L. And lastly, which I know, or it's just I don't really simply here, is that the object will be diminished. It will be smaller than the image will be diminished to be smaller than the object. Yes, now having real, inverted, diminished, formed between C and F. You get that? Now let us try using the same protocol to get for and then I don't get and the focus. Yes. For mirrors. First ray strike the mirror, pass through the focus. Second ray goes straight through the focus, passes down. If there to be lenses, there are ways you do it and you have to still engage the curvature. So here, strike, have this. You can see where this is formed exactly at the curvature, same size, right? It's going to be same size. So same size, formed at C, inverted, and real. Do you get that? So let's go through the focus as well. Let's go through the focus. Have the focus. So it's only under this condition that you can engage the curvature. So the first radiation goes through here and here. The second radiation is allowed to go through the curvature. But we find out that when you try to do that, let's put the curvature here, find out that the radiation is going to be parallel. Right? You find out that it's going to be parallel. And what does this mean? That the image is formed at where? At infinity. That's the mathematical way of saying this is not going to work. So that's the one. How if the image was formed at, if the image is formed at in front of the focus, in front of the focus, you have this one, and you want to also engage this guy. You find that these ones will eventually intersect. And what are we having? A real, erect, a virtual, erect, magnified image. That's what you're going to be forming. You get it now? That's what you're going to be forming. The location where it will be formed is going to be in between the principal focus and the curvature at the virtual side. So that's what it's going to be. All right. I think I've done for most of the positions, aside from in between focus and curvature. Just going to form behind. You can see that. Oh, it's going to form behind. Going to form behind. So this one now is inverted. This one is inverted, is magnified. There's real, inverted, magnified, formed behind C. And the focus is following display the focus that's the time. Every other time it's very much working. The not form as plenty any other time. It's only going to be the focus from there. Do you understand? So that's that for that. We move to the next thing. Having done this, the next thing is to understand our formulas. Our formulas. The mirror formulas and the mirror equations. Mirror formulas and mirror equations. Today we have 1 over F equals 1 over V plus 1 over U. So those are the things that we have. Those are the things that we have. I was looking at here 1 over N equals to 1 over V plus 1 over U. F is focal length. V is your image distance, U is your object distance. And also one side you need to know that M is equal to what? To V over U, which is equal to negative HI over HO. Where M is magnification, image distance, object distance, image height, object height. Do you understand? So that's for that. So what else are we having here? So we are going to be solving questions with this as time goes on. Yes? The image concave as in which values? Negative, yes. Whenever your image is formed at this side, be expecting your normal positive values. When they are formed at the other side, which is only under that condition, that's the only time you're getting negative value for. Understand? Another thing is the placement itself and how you decide to solve. Because I could place this same setting I'm doing now. I could mirror the setting. But I could place my concave mirror in such a way it's facing like this. I'll be doing myself from here. I get what I'm saying. Characteristics of it. That's the characteristics now. Okay, like this. Now, all convex images form virtual image. All your convex setups form virtual images. They all form virtual images. It's the general something. So we are moving into lenses. Now that we're done with mirrors. Lenses. So lenses on their own now are different from mirror in the sense that we have two visual sides no coating, two visual sight, and that's what brings about the three types that we have. We have the bi, we have the plano, and we have the what? And we have the unilateral. Let's come on. So here now, if we talk about the bi, we're talking about, maybe imagine we're talking about the biconcave, talking about this. It has two concave setups. Then plano, talking about something like this. Right? Unilateral is a combination where you're having one, that's where you use lens maker inclusion. Maybe one side plane, the other side like this. I see that now. So this place is using the convex mirror and convex lens setup. Here giving like a concave lens setup, and that's where you're using combination of lenses to lens maker inclusion. What do you review then? All right. Yes, which is combination of lenses. You can also have some situations too, composite situations, where you intentionally place a biconcave with another one. You can still come across that and use. Once you see combination of lenses, you can do what you use lens calculation. So normal lenses, let's work with the normal bi-symmetrical lenses. It's important for us to know that this one here is called a concave, a convex lens, but is what? Converging. Unlike mirrors. A convex mirror is the diverging place. Concave, which in this case now is one that is now diverging. So that's for that. That's that for that. So good. Good. So we can now look at the equations, but let's look at the setups. This guy also has his principal axis. This is the pole. Then we have the focus, that focus, curvature, curvature. How do we work with this one? Imagine you have the object here. First line to this, and it converges at the focus. Second ray goes from here, passes through the pole, probably didn't measure this, because this is supposed so I probably didn't measure this, because this is supposed to be formed behind. The way they formed is similar to exactly how the orientation was in mirrors. 100% similar to how the orientation was in mirrors. First division, straight up. The other one goes straight through pole. Third one focus to the mirror lens, then diverges. Do you get? That's what the setup looks like. That's what the setup looks like. Yes. Yeah. Right. So what else? We can now do for concave.
This two focus and down for the like one is virtual, both of them are real.
They are both one still virtual. Because in this image, everything formed here is the real for lenses. Anything formed here is virtual for lenses. Diverges. Do you see that? I said diverges, sorry. Now see, it's going to go this way. The other one, that radiation is supposed to go through this side to this side. Bend. I didn't hear you. This other radiation that is here is supposed to go this way. It bends this way. We continue this thing here. I noticed that it was going to come and intersect somewhere. If you look at it, it's coming like this. So it's going to intersect somewhere here. So you see, it's still going to be doing all these virtual things. Virtualness. So that is. Alright. So that is. What is it? No. We're about to use the equations. The equations are still the same. Still the very same equations. What do we have? These are focus, focal length, image distance, and what? Object distance. Yes. But we don't, it depends on what method you are using. We have two ways of solving. We have real is positive, and we have what? Cartesian geometry. So anyone who works for you works. Some people already put the minus in their formula because they like to use real is positive. So anytime they have real side, anything the real side, they are trying to do what? They are trying to make it a positive value, virtual make it a negative value. So people are using Cartesian. Anything to the left is what? Positive. Anything to the left is negative for x. Anything to the right, positive. So people use that too. Anyone is going to give you the appropriate. Yes.
These three remains
V is still your image distance. Object distance. You have H I still. Image height. H naught. Object height. It doesn't change. It doesn't change. Now, every single one of these people who are talking about here, whether they're less or whatever, you have something about God, a refractive index. You have something about a refractive index. We're not going to go there now. I'm going to use it to derive parallaxial law of light. But I think I'll do that in time. So good. What do we really have? we have the lens maker. That lens maker equation needs us to know the refractive index of the two lenses that are combined. And there are rules to this combination too. There are rules to the combination. Actually, what are those rules? When identical lens we use positive. But when we combine non-identical, use positive, negative. Non-identical lens we use positive, negative. Yes. This is the question. You solve one very soon. Let me just look for one now. All right. So what is our next dimension? F equals to what? So that it ends N1 over N2 minus, since you have N1 over N2, to be like that there. Okay. Yes.
It seems double format there is middle class of the fact.
Mm-hmm.
The radius of cover has radius of cover top is centimeter after the 20 centimeter of
Okay. So you wouldn't give us the refractive index of the combined lens. Like they didn't give us two. So that one gives us now having F equals to what value? The identical lenses. So we're using stick. So the one that is infinity will stand. We're not using it. That's that effect that we have put. So we're already having what? Minus 1 over what? Minus 20. So we're having 2 over 40, have we? So we're having 2 over 40. Okay.
So, any other question?
The radius of curvature of the two surfaces are close, 25 centimeter minus
25 centimeters.
plus 25 half.
Okay. Are they identical? Non identical.
Last day, can be back
Yeah.
two surfaces are plus 25 centimeter. Calculate the total length of the lens.
That means they are identical. Anything that give you plus 1 and minus 1 means they're identical. It means that they're identical. It simply means this surface is facing here to one side. The other surface is facing the other. That's why they, as mean they were not identical. That means the other one is facing like this. You will have two of them cross because they'll be pointing to the same place. That's it. All right. So yes, let's talk more question. Anybody? You have a question that you want to solve? No. The question, the complexity of the questions only come in when you don't know how to work with your sign convention. When you don't know how to work with sign convention. Let's take one of them. Because look at it's a normal sum. Imagine this is the ground, and these are two surfaces. We are looking at them as two separate surfaces. One is facing like this, convex here. The other is like convex here. Obviously, I hear you. The what? The rule. The plus and nothing is not for the value you are putting. It's for here. I didn't change anything here, I didn't change anything here. If they give me separate kind of bodies, I'm going to use what do you call it here? Plus here, regardless of the sign they will put in the object. Do you understand? That's it. Okay. So now we are looking at another aspect of this optical instruments. That's what we talk about application of optics. For them, we have to talk about the aberrations. Aberrations. Aberrations are defects. They are referred to as mirror defect. Sorry, lenses. Lens defect. Lens defect. 2 years. Lens defect.
No. This is defect to the lens, not the eyes. Doesn't have a lens in the eyes. Like a lens. Normally, if I let's strike this, they are all supposed to converge at this place. But when there's a defect, the fact that some are converge here, and I will converge here, I will converge here, and I will converge here. They did not converge at a single point. That's why you know that this lens has a defect. We cannot focus on that on the particular point. And that has a defect. Yes, that's very aberration. That's common aberration. That's two major ones. The other ones include astigmatism of the lens, which is the conical aberration. Okay, that's conical aberration. So, there are no equations for planar concave. Can check anywhere. There's nothing like equations for planar concave. Right? The planar concave, they don't used to use them. Listen, they exist based on types, names, classifications. But in application, maybe you don't use it for anything. Your planar concave, that's like half of the concave like this. Don't use it. So, all right. So what? No, let me first. Let me first solve more questions. Refraction. Refraction. So refraction is about what? Bending of light when they cross the boundaries of medium of different densities. What is it? So when it was the values of medium of different densities. Do you get that? So that refraction now, that's what we're dealing with. Those experimental observations will tell you if you took spoon inside a glass cup, it looks like the glass cup is broken. right? You know why it didn't break? It's because it crossed the medium. So the speed, the certain property of the wave of the light will change when it crosses the medium. Example is the speed, right? Example is the speed. The speed will change. The density effect on the speed will cause the wave to either move further away from the normal, closer to the normal in those regions. So that's that for that. That's that for that. So the major thing you want to understand about refraction is whenever you cross a denser medium to a denser medium, the light rays move from a lighter medium to a denser medium. The light rays speed slows down and that brings it closer to the normal. Closer to the normal in the denser medium. But when you're moving the reverse form, it takes it further away from the normal. And yeah, that happens with critical angle and critical internal reflection. All right, I'm good. So that's what goes on, those aspects. All right, so now, we are imagining we have two medium, medium 1, medium 2. Let's say medium 1, less dense. Medium 2 is dense. Because this denser is going to bring you closer to the normal. Doesn't mean it was less dense, take it further away from the normal. This is supposed to be the normal axis of travel if it didn't cross anybody. So yes. 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 Snell's law is the law for refraction already now. So he says that what? Snell's law is the law for refraction, sorry. So we can say the angle of incidence, first of all, is generally equal to the what? If it's to be your normal law of reflection, and you have this, it's equal to the refraction, in this case now, sine of our angle of incidence, I get you now, all over sine angle of refraction is usually equal to something called ANG like this. But from that knowledge that we can get more information as regards what we've been doing. All right. All right, so in this refraction aspect, one of the things we want to look at there is total internal reflection and what? Critical angle. And critical angle. It's projected, you can just off it. So I can use the board. You should just off it. So the total internal reflection only happens under any conditions. Two conditions. First condition is that what? The rays, that's incident radiation, incident ray, must travel from where? From a denser to a less dense medium. That's condition one. Condition two is that what? The angle of incidence. The angle of incidence must be greater than the critical angle. Greater than the critical angle. That's the question. So let's illustrate it. This is dense, less dense. So this is human, but because this is dense, this is less dense, this guy gains more speed that takes him further away from the norm. Yes. So this is angle of refraction. So yes, the more you increase the incidence, that brings him further opened. Because it's incidence one, incidence two. The more this guy is coming closer to the what? To the boundary. So that particular time that it took it down and it happened to now be here on the boundary, that angle of incidence is called critical angle. So critical angle is the angle of incidence where the refracted angle is 90 degrees. So the critical angle is the angle of incidence where the refracted angle is what? 90 degrees. Okay. So the moment you now take this in, if it's critical angle here, the moment you just tilt it back by even the smallest possible unit, once you start experiencing that this area of 90, I was refracted area of 90, will now become fully reflected. Fully reflected. So that one now is why we said the angle of incidence must be greater than critical. So this critical ones, open it again, you have full reflection. See, it's not a big deal, it's not hard at all. It's not hard at all. It's very simple. All right. So, timekeeper, how many minutes do you have? So, okay, 20 minutes to get. Okay. All right. So, from here now, what are the effects of total internal reflection? Number one, it has effect on optical fibers, positive effect on optical fibers, and it creates road mirage. What are road mirage? What are road mirage? When you are driving on the road, there's a way flow in front of you looks as if have you seen where people are turning for you? You see the people where you are turning for the region where the problem. That's at the front of the road you look like. Okay, I'm about to enter another road. But you never get to that. It always looks like it's in front of you, but you're not entering it. That's because those radiations are interacting between what is the denser part in the atmosphere, and they are moving into the what? Into the less dense atmosphere in the lower region, the region closer to the land. And also there is total thermal reflection downwards between the hydrated atmosphere or due to humidity or rain and the clear air at the lower surface of the earth. That's what causes it. Then optical fibers, and those ones on end, when there is full reflection, it supports their own reflection of signals. Well, they work via reflection, optical fibers. They transmit signals via reflection. So that's like an additional momentum that helps to propel their signals and reduce signal transduction. Any question? Okay. Optical lens. Optical instruments. So we're looking at optical instruments. So that's when we are applying all our knowledge of optics into the science, into different models design, and bringing combination of lenses to support so many things, ranging from being able to design a telescope, to being able to design a gyroscope, to being able to design normal binocular lenses, being able to design correctional lenses, medical correctional lenses. Okay, and also a microscope. So we'll see how the lenses combine. So to start with this, we need to look at the human eyes. You need to look at what's going on in the human eyes. But the human eyes have as a model. For so many of these things we talk about, it's very difficult to fit the eyes. Okay. What does our normal human eyes look like? What does it look like? So what is it? Yes? It look like talking about the image. You have something like this, after the minute, you look at it, and this is you have an extension here, still extension here. So from there, you have the retina lining this place. The retina. That is line also that hold the lens. It kind of this is a sharpish diagram. I'm not making it too detailed. Because what you want to see is this space, this lens. I want to show you how that converge, how the defect occur. So the two most important things we need here are these layers, because this is where the image gets formed on this side, retina. So basically, when light travels into the eyes, This lens here is a concave, convex lens. It's supposed to do what? It's supposed to converge it, abi? But the correct conversion is that it converges it on the retina. So two possible defects can happen when it's not able to converge on the retina, rather it's converging it at where? Before the retina, that's before the retina, or converging it behind the retina. When it converges it before the retina, call that one myopia. After we call it hyperopia, but people call it hypermetropia. So that we have used to this. So to correct all of these things, you can see that this one means for this thing to converge and not converge here, it means its converging power is too great. We need something that will reduce the converging power. That means we need something that will open this place to be like this. So that when it converge, it will not converge here again. That's why we need a lens that can do what? Diverge the image before it gets to the lens. So that the lens will have a travel converging. To converge it. So there are many calculations we use to do that. Okay. 15 minutes. What does somebody talk just a minute? Jesus. See me thinking that we don't understand. So yeah. You now put the words. If I want to correct this one now, I need to put something like this here. So that before the ray of light enters, it will do what? It will diverge. So when you want to convert it now, you see it now. So they will have done the calculation to know the power of divergence they want around here that will balance what power of convergence the person's present eye is doing. Because they are not correcting your eye. They are only helping to regulate the kind of light that enters into your eyes. Is that clear? So that's for that. That's that for that. So if we were going to correct this one, what do you think we need? That means people that have this kind of issue when it is converging behind. That means the person's lens is not powerful enough to converge immediately. I get it now. In most of those kind of people, their lenses are thin. Their lenses are thin. In first case, how do you
See, where are we now? Aparopia. So what are we doing? We look at the condition of the myopia. We said we needed extra divergence before natural convergence, right? Then for the hyperopia, what do we need? We need a more powerful convergence. We need a more powerful convergence. Get that? A more powerful convergence. So that we converge it, even before you get there, so that you cannot converge it, so that we now be able to form at the right port. So you write down the hypermetropia or hyperopia is corrected using what? It's corrected using converging lens, which is convex. That is convex lens. Then myopia is corrected using what? Diverging lens. That is concave lens. Yes. All right. So that's for eyes. That's for eyes. Let's now go for telescope. Telescope. No. Everything asleep. All right. So what the telescope is? For children, a telescope is an optical instrument with high power magnification. It's high power magnification due to a combination of lenses. Due to combination of lenses, yes. Due to combination of lenses. Due to combination of lenses. Now, the thing is, apart from optical instruments use, the characteristics of them, they will have an objective lens. I get it now. But have an objective lens. And the magnifying lens. Some of them use concave and convex. Some use convex and convex. But we need to know what each one uses. So, what lens does the telescope use? How many lenses does the telescope use? How many lenses? It makes a minimum of 2 lenses. There are some that are open up with multiple layers. For minimum of 2 lenses. Minimum of 2 lenses. Something like this. That's what it is. Now to ask you a question, because we need to know let's do a combination. Before we will start drawing what's going on with two lens, one lens and all. Now, if light travels like this, if light travels like this, and now this one, and let's imagine that this one's focus. This is one. Watch me. Watch me. What's going to happen here? When you get here, see, they are allowed to move continuously. Some move there. Some move there. When they get here, what do you think they will do? They are going to diverge. Diverge and be converged. It's just that if they were like this, they'd have converged to focus. But now, they can't converge to the focus. Where are the converge going to be? It's going to be slightly like this. Same thing with one down. This is what it will look like if you combine two lenses like that.
Okay.
I mean, while you are combining so if we have the position like this, yes. I'm not started showing how the image will be doing. So when they get here, what does this one do to it? It's common sense. When you look at this surface, what does this surface do? True of us. Understand? So I'm going to look at the first scenario. It's question style.
Fill out on our spots. Hotspot.
For
Camera.
We'll see the camera. Those ones are normal.
so I want to give illustrations.
We use like 4 illustrations because now we have to put images at specific positions, viewing through the telescope, and see what product, what kind of image we're going to get from it. If it's going to be a very magnified image, we'll compare the magnification with the original size of what we do. That's why we're going to be using smaller size images. Okay.
Okay. So we just inside images. Just the right of product. One permanent representation or reproduce one. So that's one for
Those are not coming. They're not coming to church. She has gone far. She's only gone far. And my phone is on video. I don't know speech.
okay, so trying to load
Images.
so right now, right. Giving, I told you the telescope related to view was in space. So giving that light, giving that light, picks up images from a point in infinity. Giving that light picks up images from a point in infinity, a point at infinity anyone. Using a telescope setup. Using a telescope setup. Obtain lens diagram. Obtain the lens diagram. Obtain the lens diagram. Utilize viewing the image. Utilize viewing the image. Utilize viewing the image.
So yeah. So now, telescope use it to view things in space. We use it to view things in space. So our image, the object, is going to be coming from infinity. Let's just imagine that we have one here. The bigger convex lens will be here. The one for the eyepiece, somewhat here. So let me put the focus of the first one. Maybe I have the focus of the second one. So let's imagine that from infinity, the object came, the radiations came. When it gets here, what will happen? Convergence, I mean. But whenever there will still be a part of the radiation that must pass through the pole. And whenever radiations pass through pole, there's no effect. But that means that one won't come straight. When this one has already done what? Converge. It's converged. And increase what this lens size looks like. So converges here. Okay, when it does that, imagine the eye person, the view from here. It's going to happen such that it's going to happen such that the vision will converge to the eyesight of the person here. So it's that simple. Sometimes they might use the real environment where an imaginary side of the light wave also propagates from a straight line from the person's eyes, straight line of his eyes, and also from here. And this place where the intercept is where the image will not be found. An object of infinity. And what is it? You know what? It will be formed between the two legs. This is the eye piece. You understand? It will form in between the two of them. So please can I write that down? Now, how about if you want to do something in space? You want to just do something on the planet here. Maybe something small. You want to see, just get a proper big view of it. That can be something. What do you do? That one now means the object will still be on the axis, I mean. Let me not make it too big. So let's imagine this is where the object was. As in now, we follow the same rules. Yes. Yes. So imagine comes here, it deflects. So what happens is that if your eyes receives it here, that region will continue downward like this. So continue, this one is continuing. They will eventually intersect. You look at the way I did it. This one went like this, this one went like this. So they will intersect somewhere around here. And you can see that the image that we formed will be bigger compared to what you had here. You get? So that's how the setup is. Let me cover. That's how the setup is. That's how the setup is. So basically, it's similar to what? Telescope. So a telescope lenses are more powerful and receiving images from infinity. This is microscope. This one is for microscope. This one is for telescope. Right? And I've done one of the members of the gyroscope earlier on, which was the kaleidoscope. So that's those ones. What's next there? After optics is what? With theory of lights. So the way theory of lights okay. So what is the wave theory of light? This is the branch of physics that is trying to explore or explain the properties of light as a wave. We see light as a wave. You know, there's a part of things that describe light as dual, both as a particle
and as a what? And as a wave. Now, we want to check out light as a wave. And there's some theories that they put forward, and some of those theories were not able to be proved, they were disproved, why some still hold true now, and that's why light is still subject to paradox. So we're going to be going through all the theories that have been proposed about light, the limitations of some of those theories, which are like the setbacks, and then we from there take advancement into modern physics. All right, so light exhibits dual nature. Light exhibits dual nature. Light exhibits dual nature. Both as a wave and as a particle. Both as a wave and as a particle. Certain theories suppose or describe light as a wave. And some others describe it as a particle. And some others describe it as a particle. One of the theories we're talking about the Guinness principle. That's where it will start from. Where we have to understand that each wave, like your waves, have wavefronts and has tiny particles that have the capacity to build new waves that we call wavelets. So we need to understand that structure first before we even start diving into the nitty-gritty of light per se. All right. Again, Huygens principle. Huygens principle describe that a wave has wave fronts. Have waveforms that are made up of secondary wavelets. That are made up of secondary what? Wavelets capable of propagating. Capable of propagating new waves. And the way they propagate are what kind of waves? Spherical waves. So that's the same every point on the wave act as the source of secondary waves because of the presence of wavelets. For example, I will ask you, what are the wavelets? What do you answer? What are wavelets? Wavelets. No. Wavelets are secondary structures found on the waveforms that have the capacity of producing or propagating new waves. They are the ones that can produce the new waves. They are not
So it's theory alongside with Thomas Young theory is what they put together to start the fraction grading. Since they knew that, oh, this way forward can produce new wave, they now want to try to bring in principles that can help us to experiment on the waves produced by the wavelengths and see how they can form fringes. That was just to prove interference. So right. This theory alongside with Thomas Young's single and double-slit experiment proved interference of light, which is the waveform. Proved interference of light, which is the wave property. Hi there. This interference will of two types and form either dark fringes or bright fringes on the screen. And then the constructive interference gives bright fringes on the screen, while the destructive interference gives dark fringes. And now, imagine you have a wave. You have a wave like this. Imagine you have a wave like this, traveling like this. And you have the source of another wave like this, watch. Another wave. Let me just say, we started from this place, this point here. And from this point, we have another wave propagated from here. Look at this. Every single place where the lines intersect, every single place where the line intersect is a what? You see, I can draw a line like this. I don't just draw this properly. Normally, if you draw properly, you see that you're able to draw a line across those places where it intersected, right? Those places, the screen, when those places try the screen, all you see is dark spots. While all this place here, we form what? Bright spots. That's from a spherical point of view. You can also notice it from drawing view in this fashion. When the little screen is, and I have another wave like this. Obviously, that will form a constructive interference, and that constructive interference will do what? Because the spot on the screen, when the incident on it to glow, forming a bright fringe. Forming a bright fringe. Forming a bright fringe. Okay. So right. Join that. Make sure that they are in peace. I'll remind you. I'll remind you. What does it mean? So how about relations like this? What does it form? What does it form? That phrase, I mean, because these relations were out of peace. They are out of peace. They will form, they are going to form destructive interferences. Okay. The phase difference between the two waves, the phase difference between the two waves also serves as the determinant. Also serves as the determinant. Also serves as the determinant as to also serves as the determinant as to if the resulting wave is destructive or constructive. So, when the phase difference is the whole number of wavelengths, when the phase difference is the whole number of wavelengths, and the phase difference is the whole number of wavelengths. The interference is constructive. The interference is constructive. And if it is a fraction, if it is not a whole number of wavelengths, then it is destructive. Okay. So, the first theory we'll talk about now, the light theory, is about the ultraviolet catastrophe. But in the syllabus, it's like one of the mentioned syllabus. You have a copy of the syllabus. You have a copy of the syllabus. Okay. So we're going to treat them again. Talk about difference. Okay, what does it mean for a wave or two waves to be coherent? What does that mean? What does it mean for two waves to be coherent? What does it mean for them to be coherent? Let me just show you. Two waves are coherent if the two was if they are propagated with the same source or a phase during their propagation. If they are propagated with the same source or a phase during their propagation, then we can consider them coherent waves. So what does that mean something? There's no even lazy laptop. I don't use your phone. Okay. So before you even see two waves can form constructive and destructive. First thing that must be peace. And person. Peace. I get it now. What is the difference between interference and superposition? What is the difference between interference and superposition? For interference, the wave does not need to come from opposite direction. Yes. They really don't need to come from opposite direction. But it's superposition the most. It's superposition the most. Let's continue. The next thing is so write young double slit experiment. It's not illegal. Alright. Young double slit fringes. Young double slit fringes. Now, if you have a single fringe,
If you have something like this, this is the slit. There are certain conditions that must be put in place before diffraction can occur. One of it is that the size of the slit must not be, the size of the slit must not be less than the wavelength of the wave propagating through it. Although the greater than, it must not be greater than what? Than the wavelength propagating through it. For those of you that are reasoning this one, there's the difference between diffraction grating and young double slit experiments. They are not the same thing. What we are looking at is scientific experiment that helps us form things like this. Each of these things happening like this is usually happening because of how the waves tends to spread out and what each of the wavelengths lets produce and doing to the wave. You get that? And one of the things it does is that it forms repeated dark fringes. That's the one I showed you here. Where you can trace some lines where you have dark spots and some where you have bright spots. You're getting repeated bright fringe, dark fringe, bright fringe, dark fringe, like that. And all of them we have a diffraction order. We all have a diffraction order. Do you get it? So the greatest order is one that is directly opposite to the fringe. So let us imagine that we have a line drawn from here like this. And we have another one that goes to the second order bright fringe, the third order bright fringe. No. I'm not going to talk. Yes. Okay. What was the let's go. Very good. So your black fringes is talking about just places where constructive interference occurred. Dark fringes are places where you had what? Destructive interference. And I say that as would, especially in that diagram. So, right. The fringes can appear in two forms. The fringes can appear in two forms. Depending on the nature of the diffraction. Depending on the nature of the diffraction. Depending on the nature of the diffraction. So sometimes we have a single source diffraction that goes on to collude with a double source diffraction. And there you have that plate diagram that I drew. As I said, just okay. Now look at this. Imagine you have a single source of wave, and the wave now traveling through it, something like this, right? This is for diffraction. You now have double slit. You now added double slits here. What happens is that by the time the wave comes here, each wave will be able to do something like producing its own wave, right? And the same thing this one is doing. They do it continually. Same thing with what this guy is doing. So we're not going to imagine. So yes, we're not going to imagine it strikes the screen here. This region here you can trace this dot continuously. You know, this thing could continue. Let me just show the continuation, but round, where you could trace this continuous dark spots. Shows that one terminates as a what? As dark fringe. Terminates as a dark fringe. Terminates as a dark fringe. So yes, but a more practical way to look at it is to see the wave drawn in the places. Because if you do this in your exam and you draw it counting, which examiner will take the time to come and check it? Nobody's going to come and count and see if you know you're doing. So what people present is that you draw a single wave and make sure you count how many wavelengths are there. 1, 2, 3, 4, 5. From this place, I have to draw it in such a way that it will be more than 5 if I'm trying to describe my presence. So I can have 2, 3, 4. So let's check something. This is 1 wavelength. Abi? 2 wavelengths. 3 wavelengths. 4 wavelengths. 5 wavelengths. Let me say I stopped at here. This is the place I stopped at.
So one wavelength, this is one wavelength here. From here, 2 wavelengths, 3 wavelengths, 4 wavelengths. How many did I count for this person? 5. How many did I count for this one person? Then each of them have half remaining, Abi. So that means the 2 of them differ by how many wavelengths? 1, Abi. That tells you that what you have here is what kind of fringe? A bright fringe. Because the difference in their phase, that their phase difference, that their path difference, differs by a whole number of what? Wavelengths. That's how it's a bright fringe. That's how they demonstrate it. They don't demonstrate it with that line. That line only gives insight as to what you're supposed to expect. All right. During is split experiment. During the split experiment, for interference to occur, the waves must be in phase with themselves. Must be in phase with themselves. Must be in phase with themselves. How do they must be in phase with themselves? And now that being in phase is like condition 1 before you even start talking about what kind of interference it was. So once they're in phase, that means interference can happen. You understand? Then what kind of interference happens now depending on their what? Their path difference. Alright, so the path difference means the type of interference. Whole number path difference is what? Constructive, forms bright fringe. Do you understand what I'm saying? So good. Now, this experiment was not carried out properly by utilizing Fraunhofer lines. I get it now. We have only Fraunhofer line 2. What are 2 Fraunhofer line? No, not fringes. We have the single slit Fraunhofer diffraction, and we have the what? Double slit Fraunhofer's diffraction. You are not writing. Now, both of them have something we call the limit resolution. Now, for the single slit Fraunhofer line, right? When parallel ray of light, propagates, with wavelength, incidence normally upon a slit of width d, a diffraction pattern is observed beyond the slit. A diffraction pattern is observed beyond the slit and is dependent on the order of diffraction n. If you don't already before the class, we're doing the topic. So what is the formula now connect them? M equals to what? D sine theta. You can write it down. M equals to D sine theta. D sine theta. So example.
on that single particular diffraction. Right. I'm coming on to get it there. Okay. So the chicken is so clean. Go for right. Red light. Red light pulse value of the diffraction grading. Red light pulse normally on diffraction grading. Root 4,000 lines per centimeter. Yes, we know. Red light pulse value of a diffraction rating root 4,000 lines per centimeter. And the second order image is diffracted 34 degrees from the norm. 34 degrees from the norm. Compute the wavelength of the lines. Compute the wavelength of the lines. So that's all. Yes. And everybody got this. Anybody? No, you got. Your formula was what? 2 lambda equals 2. It said second order image. Abi, what do you use before? One. Yes. So, you know, this one, they give you the line per centimeter. They 4,000 lines in every centimeter. When they give you 9 per centimeter, that is generally, this is what you're supposed to do. 10 lambda, that equals to A centimeter. Where A is centimeter per line of the grid. So the truth here is that they give you the line per centimeter per line. That is the unit of the 2 lambda equals to 104,000 sine 34.
What is your calculator and find wavelength? What did you get? What did you get? You don't know your person. Don't know what you're doing. So, any sign as a police works. Okay. That's it. So the answer you now get is 6.99 times 10 centimeter. Original convert. Okay. Let's see this one.
That's all.
Okay. So a parallel beam of X-ray is diffracted by a rock salt crystal. The first order strong reflection is obtained when the glancing angle is 6. When the glancing angle is 6 degrees 15 minutes. How many of you know to write that 6 degrees 15 minutes? Degrees. The distance between reflection plane. The distance between reflection plane and crystal is 2.8. What is the wavelength of this ray? Convert it to degree. But I've forgotten the rate of that conversion. I think it's just 0.01. 0.01 degree is 1 minute. So that thing will just be like 0.05. Check.
When I say we answer the question, no problem. The video will be showing that they are solving. 0 minutes. Yes, thank you. Which one? What about the question? Question. Like the one of, this is the one I saw before. I thought I saw it. That's the one I saw. Okay, about green lights. No, it's not about green. How's that? I don't like the answer. What's that? Okay, so still solving. 5 seconds. That was not it. So, we gave you the separation as 2.8. So we are doing bounded equals to 2D and theta. Because this is S read now, diffraction. S read diffraction, first order. The parallel beam of S read is diffracted. So that's what we have to do. The D is 0.66. All right, let's go on.
Okay.
Green light of wavelength 50, of wavelength 4, 540 nanometers. Green light of wavelength 540 nanometers diffracted by a grating road with 2,000 lines per centimeter. It is diffracted
migrating road with 2,000 lines per centimeter. A complete division of the third order image. B is the tenth order image possible. That's all. Not actually. Green light of weight is normal. And using that name. Yes. How many years was it? How many years was it? Part B.
Sending it on to 0.3
1.0. Which is the 10th order image possible. The 10th order image possible. No, it's gonna exceed one. Okay. All right. So, let us move. A drum seat. A drum seat. A drum seat. experiment is done in the usual way with 418 nanometer lights. The dosage is done in the usual way with 418 nanometer lights. And now Smith announced it that are 0.05 centimeter apart. Full stop. At what angle to the central axis? 0.05 centimeter apart. At what angle to the central axis will one observe A, the third other bright spot? The second minimum from the central axis. The second minimum from the central maximum. Alright. That's all. Was it? Zero point 16. How many zeros? Take. Okay. So check what you have to touch first. That's not know. I don't know. Alright.
It should be. When did you come? Yes. Oh, no, you don't.
Alright. Alright.
What do you want to talk about? Oh, yeah. About what? No, let's see. What do you want? I'm seeing that. All right. So we move. The next thing we'll talk about is limit of resolution. Yes. We want to learn how to limit resolution of two objects due to diffraction. Now, right, if two objects are viewed through an optical instrument, the diffraction pattern caused by the aperture of the instrument, the diffraction pattern caused by the aperture of the instrument limits our ability to distinguish the object. Limits our ability to distinguish the object. Are you there? From each other. Limit our ability to distinguish the object. They limit our ability to distinguish the object from each other. Thus, for distinguishability, the antenna suspended at the aperture. The antenna suspended at the aperture. The aperture is open due to the slit. The opening due to the slit. The antenna suspended at the aperture by the object must be larger than the critical value theta subscriptia. The critical value, which is theta subscriptia. Theta, you just put subscriptia after you use critical value. And that's the formula of the zone. What's the formula? I know you. Should be equal to 1.22 G. D over lambda. CR, that's something. CR. Equal to D, sorry, R over D instead. Because this will be larger. Then what? This is the normal distance now. The distance from the aperture to the screen. There's no area. This wavelength. This wavelength. Wavelength. So that distance, you know, the same thing as that distance from to the place you view to the screen. It's still considered the size of the that is the diameter of the aperture of the camera. Just in case. Let me see if I can see a question of that. Stop it. Stop it. What? All right. So let's do this. A single slit. A single slit of width D. A single slit of width D, which is equal to 0.1 millimeter, is illuminated by parallel lines. Is illuminated by parallel lines of 600 nanometer. And diffraction bands are observed on the screen. 40 centimeters from the screen. How far is the third band? How far is the third dark band from the central bright band? And lambda is equal to D and theta. The prior unit is given already. Everyone theta, which is theta 3. Not this one, it's not from this one now. I didn't hear you. Which end? M. L. Which end now? Is it M? M is 3. M, normal order of diffraction rating. G. No, no. Yes. 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 Okay. All right. Let me see something again. What else is there? No good. Syllabus. I thought about this one before. Yes. All right. So we're here to electrostatics. Electrostatics. Let me just start. So okay. So we are going to electrostatics. Now, what's electrostatics? You can break the word down and you see what I was. The electro stands for charge, static means rest. So it simply means study of charge at rest. Electrostatics is the study of charge at rest. So when we say charge at rest, we're looking at charges that are not moving, they are just stagnant there, right? And that brings us to the types of charges that we have. The type of charges that we have. We have
So we have positive and negative charges. What are positive charges? What are negative charges? Positive charge and negative charge. So the positive charge, it is one that tends to be polarized towards negative electrons. Also, these are charges from which electric field leaves organized order are released. While negative charge are those in which the electric field enters. And positive, we have negative. For a positive field, you see lines like this. So from here, fields are directed inward, where field leaves.
This is what we happen again. Right? Because these two can't give themselves charges. You need a system when one is ready to give, the other one is ready to do what? Receive. Both of them cannot give themselves charges. Same thing if it's negative, it will repel. It's only online charges that attract. Positive, negative, you have something like this now. So it satisfies the both of them. This attraction. This attraction. So both attraction and repulsions are forces that are felt by electric point charges. Understand? They are both forces that are felt by electric point charges. So good. So if we're actually there, so when we're there, I wanted to understand how forces attract themselves. Let me use the two systems, so I'm not confused. This one, this negative charge will be creating the force of attraction on this body A that will create a force that wants to propagate to himself. That force we call it F in B, which is force on body A by body B. Same thing happening here. Force on body B and body A. The same thing is true for repulsion setup. I feel the force pushing back. This force is FAB. It's the force of repulsion that is acting on body A as a result of body B. What's the one this one? Force on body B due to
or the A? So that's that. That's that. The next thing I want to understand is the acronym is F. So what do we have from here now? Simon 2000. So, whenever they ask questions from this, you need to be careful. This one is from gravitational force, Coulomb's law of electrical force. Coulomb's law states that what? That the force of attraction or repulsion between 2 point charges is directly proportional to and yes. For permissivity, for permissivity. So I have this. Okay, formula. So we're not having what? Okay. That's it. No, I'm not going to it. These two, they are solving this difference. So from there, from there, I'm going to expose ourselves to some kind of questions. I'm with vector analysis. So let's take for instance that we had a charge here, positive charge, one charge, a negative charge, and then another charge here. Positive charge. This is just 5 column. This one. Yes, net electric field. So the first thing you want to do here is to analyze the vector. So let's imagine they told us to obtain the net force acting on the 4-column charge. So we start studying now all these things, all the other charges, and this one. Again, so what do we do? This positive charge, what will we do to the negative charge? It will be attracting them. So that's our because the level because trying to attract. Right? This one, what will we do to the vector, to this charge? This is not very good. This one is attracting this one along the line motion. The action is along the motion. If it was red, I would push it away. But I'm attracting. To bring it down the vector, you saw it there. This was the question I was just saying. So let me just imagine at the beginning of this year, I'm coming from here to here, 40 degree, I do not get you. What do you 30 degree, but I do like this and like this. That is, here is what, and here is what, 30. So I was doing resolution. Which result is what the x-axis is positive. Result to the y. This result to the x. Result to the y. Solution. Five point 66. Alright. So now this, you have to find equals to. Is that the way to find this? Everything goes. 3 points. Which one? Everything. I don't know this was this is the force. It's the force. It's part of this. Yes. Yes, you need to check out the line of action of the vector. Moving on. So there is one during this. So It's not when results in what do you do? The time you check the effects of these three people on that person. So I didn't put in the challenge. It's a positive one. But I'm not really designed to solve. I'm not supposed to put this down. No, I shall not put it. I shall not put it. Yes. Do you know that? No. Watch. This is a positive charge. Okay. What charge is this? They ask you to find the force or the fourth one. They are talking about the car. Now the initiative force is there. This one and this one. What kind of force is there? And this one. Repulsion. So that's why this is let's call it one. This is also repulsion two. And again, so we need to know this force is everyone. What to visit this and we need to distance. We need to know this one is true. You get it? Yeah, people can resolve. Everybody because the dream is opposite. And also, this. Use this formula. We get this particular and you get it. If I truly want this one, choose this one. This time to do is this. You still do this for something. Sometimes I always do it. Both times over.
First course, you have considered that is as well. And for you asking on the super microbiome and seven. Microbiome, you have 7.
Yes.
The other one, you have 1.6.
Yes. So 1.8 to 2.7. 1.8.
1.8 and 2.7.
Yes. That means. Okay.
So what's the next one?
So 60 is 60. So let's find the result. What are the possible? What was going on? So how many people do you see around the two? This and this. Result is X and Y. Then you find the result. You get it. So do you think how do you was?
You have
What was the value of them?
F is 1.8,
This one.
2.7.
So this level.
F
1.8, 60, 1.8, 760, the 2.7 was 60 minus.
second column.
Solution.
On the first one, you have minus 0.45.
0.45.
Second one, you have 3.68. Because this one has a negative value and this one has positive.
This one is just talking about the line of action. It means that if I want to draw this force is, if I want to draw the electron to look like, this is what it look like. That is our low component is 3.88 in the positive x and 0.45 negative y. So any direction we want to get is this place. So we want to go with the resultant. So the resultant is
The resultant is 3.90. And then
what direction?
left one. You have 83.38 degrees.
And this is the 3.3 parallel. You can't do that. This is east.
Because in the second one,
This is north. Sorry, west. So that is the
so we can do minus 90 minus 63.9. Now, 180.
Just 180 minus this.
Mathematics. 96.61.
Yeah.
96.61. This is basically like vector analysis.
Yes.
Next question.
The true. Compute A and the fourth column. Compute A and the fourth column. When it comes to field, they don't work actually. Field is talking about who is leading, so who is leading exactly. So from who does it becomes, from who does it leading. So we want to create the vector analysis analogy. I will look at it. They want us to take compute E as the first empty column here. So what does E negative charge do? What does negative charge do across it? Field usually enter. So what this want to do is to want to create the tendency for field to come out from here. So that I can want to enter into it. What does it want to do to it? It's safety. But in order to draw it to that place, we need vectors. Draw that. We just know that this is going to be costing field to want to come from here. What does it want to do to that place? This one gives us the we cannot draw a line from here. Everything wants to tolerate here. Neither can we cannot draw the end here. So this is the best way we can do it. Do you understand? Yes. So this is what we have. So
So stability for the power point outcomes because field leaves of the policy.
yes, different. So start. We know the formula for field seeds. So you want to get the value of each of them. You know what to do. You just pick the Q because if you want Q, see,
Only for respecting size.
You are paying for each one that is there. So this one here now, obviously to get this one here, you are doing A equals to K
You.
and I will call it the number back.
You.
Distance from here to here now. To give it here, let me check. The question. Each side of the square is 30 centimeter. Each side of the square is 30 centimeter. It's a square. And each side,
Without communication.
yes.
On the 5 microfarad, your electric intensity is 500,000.
Which one?
On the 5 microfarad. Yes.
Electric field is
500,000.
okay. So it's here that I live in 500,000. Okay.
On the 5 microfarad, your electric intensity is 400,000.
Yeah.
Yes.
What's the unit?
This is how it so,
Newton per column. The last one. Do you have the distance for the last one?
is that going to be?
No. This is the distance.
So, let me get this machine and calculator.
Yes.
The distance is 640,000, 312.4.
The distance. 640,000. You're using this one. The size you use, you are getting the distance. All these things are no distance. Yes. All these things are no distance now.
So it's 0.424. So you have 400,000, 498.4.
Okay. Is that
Yes. You have 400,000, 498.
so you can draw the vectors of the clearer.
see a question that involves including and giving
Yes. Finally, finally, is is square out. And the language into two of us. If it's truly square, we divide into two, then it's not divided. I mean, I think that's what we need. And we need, if yes, 45 minutes or so. It's for the best kind of wisdom.
Well, this one now is related to break up.
It's not time the other ones.
Where was it to stop? I didn't talk. Obviously, we can see how I'm correcting the equation. I know you have a way of like the 0. But if I can make it up musical, it's component 1 is 0.
Yes, that's plus or minus 2 0.
If I can make it up, the percent is 1. And for the 1% in the group, you have minus 400,000 plus 180.
But I didn't get it.
But it's also a 400,000 and it's direct.
What do you want from it? Okay, like the angle.
Yeah.
The angle is 0. Which is 9 degrees. So it's positive for x, negative for x, or positive or negative for y.
They have minus 400,000 and 7.
Minus
400,000 and 7.
as a result of it.
So how's the.
Okay, yes.
Okay.
Yeah.
So for the result for the commission of the X components, you have minus 116,804.8. And for the Y components, you have 783,195.13 axes. So, Dr. Kashi, are we finding the low time of the first?
Yes.
The result was the 852,822.9 Newton.
You see? Where is that something? You're sure about all these values? Minus 400, 400, 500.
500. And what about the whole like
What's the first result down to the X?
the solution of X? I have 283,195.1.
283.
Yes.
Why not for July?
But Y, I have 783,195.1.
This is your situation. Yes.
Yeah.
So, listen, when you did forget here, did you cover the microphone? Did you open the microphone?
I use microphone.
No movies.
I use my flash buttons.
That's your movies. So now having 0.00. Times 9 is 10.
9 is over 9 over 0.3 squared.
Yes. Don't give us that. Just sit down. How did you get this one?
Now we use a different
This value,
time.
this is the value there, right? Good. Times what?
That value
You just square it. Okay. So, when you resolved this one, let's start picking up x and y. For the x starting from here is 0.
0.
But this one is positive 500.
100,000.
This one for the x negative 400.
400,000. 0.
This one
And that one, we use 45. Okay, fine. Next one, we are 83,195.1.
is it
Next one, we are 83,195.1.
for which one? That's all.
Yes.
What is it? What is it?
283,195.13.
Yeah, go.
They get negative because of the first one.
Of the same value, right?
Yes. So the solution of the first one is no. They're supposed to get that for that side, the negative value of that value on the x value.
What's this one? What's the value for X and Y?
You have 268,804.87.
This one.
And then you have negative 116,804.87. The result is 246,267.1.
2.1.
246,267.1. I think this is negative one.
So what's the answer?
There's 246,7.2.
Direction, please. And we must only draw the agenda. So I don't know, whatever I get, I'll subtract it.
Yes, one message is
So 180 minus.
you have 180.32 degree.
That's not all. But that's the question, and I said, what will be the force of a 6 microcoulomb charge placed in that vacant space? What will be the force? What will be the force on a 6 microcoulomb charge placed at the vacant space?
Okay, so if this force here is 6 microfarad, if the charge here is 6 microfarad, kind force.
No, you don't need to start again. What do you want to do? Let me see.
For that distance, we will be using 0.3 or 0.424
For which?
for the empty space. We will use 0.3 or 0.4.
By using distance. I'm asking you, you are planning to use distance. Why? Have you forgotten that force is equals to EQ? We already know the E at that point. The E at that point is also true. So the force is simply 246,267.2 multiplied by the Q you want to add there. 6 times 10 to the power minus 6.
What is 1.4? What's that? What is long? What's
Um,
But you information or the
Column law. You get what? You don't really because it's column law.
That's the one to
There's only one charge. So let's deal with another problem. We'll keep dealing with problem C, problem tire. If the tire that means I'm sure you're supposed to do existing. People that have a problem will find themselves. So if you check that statement, I'll advise you. Pick one. Start loving problem now. Or by what do you write? So, problems all the time. Problems are facing everywhere. It starts with problems from the beginning. Problems.
Thanks, Christian.
So look at this. 4 equal magnitude point charges. 4 equal magnitude point charges. Tell me this. I'm not saying it's me. Yes, I've seen it. I've seen that I don't understand it. And you come to class later, you don't understand. 3, sorry, what was I speaking?
2 point charges.
Well, so you can see what she's doing. If you cannot see that me, I'm doing it, you see how she's doing it. Like, it's not doing anything. Don't go and come front, we see you scatter everywhere. They tie your chair to rope. Madam, I'm not lying, still back.
Look at this question.
Which contract scatter camera?
Question.
4 equal magnitude point charges. Remove base. You know you cannot base from this sound. Base is too much. I can't bring it myself. I'm just very too deep. I start cracking, you just increase the tweet. Stress of my legs. No. It's this. 4 equal magnitude point charge.
Okay.
3.0 microcoulomb are placed in air at the corners of a square that is 40 centimeters on the side. At the 40 centimeters on the side. 2 diagonally opposite each other are positive, and the other 2 are negative. 2 diagonally opposite each other are positive, and the other 2 are negative. Find the force of each negative charge. And so,
Find the force of each.
negative charge.
So I'm not making the positive charges.
Yes. Find the force
on either negative charge or either. Yes, you have two negative charge. Pick one and find the positive. What are you carrying calculator for? What are you carrying calculator for? Calculator is for what? You have not drawn diagram. Draw it first. Start drawing. To some and this is just down the line. I have what? 10 minutes of break. So just leave me and see what can I just do first. Yep. That's it, yes, son. But to pick one negative charge and work our force, look at the way we did this travel, check out what the forces are acting on it. You need to know. Okay, give be with me. Please, any of the projector sharp aside you. Let me off the projector, this light, I want to do that side. No. Question.
4.2 charge, 3.0 microcoulomb are placed on air of the square 40 centimeter apart.
4 centimeter
Apart.
we are using 0.4 meters.
Two diagonal, two on the first page, there are two diagonal.
All of them are 3 diagonal. Okay. Diagonal, positive,
Yes.
negative. You now have to check the effect of all the remaining charges on one of the negative. So how is this one? Let me imagine I picked this one I picked. How is this positive charge going to be affecting this one? It's going to be creating an attraction. So that means I'm going to be expecting this place to do what? Pull up, right? Now what do I expect from this one? Attraction again, Abi. How about this one? What do I expect? Repulsion along the plane of axis. So we've gotten our vector diagram. From there we'll do work. Let's go. Start. And this one like this will solve like 100 today. One analysis of this different type, parallelogram, triangle, carbon. You know, notice that today we will not log the door. I love the punishment. Whether you like it or not. Yo, come and see you from here. What is that? The wine. It's just the wine. Yes. resolving. Why not to resolve? When we are done, we want to know the net effect of all the forces in this one. Now we can see that this one is pulling them up, this one is pulling them up, this one is pulling them away. And then we will not resolve. We need to find a single force that interprets the whole actions. What is it?
But which is resultant force basis?
Yes. So, what's this distance? M. Then help me with the angle as well. Because already we know we need this angle here. So if you know this angle,
Sound is 0.5 dispatch.
you really know we need this angle.
Right.
How do you know?
Because
Because it's a square bar. Okay, so this is 45. So if this is 45, means here is also what? What's the reason? Yeah. Jesus.
Something actually
You going? The time has passed. You are staying for more than 4 hours. Rotate this girl, serious. Alternating angle here. Hello, what's the name of this kind of angles? Angular relationship. See my student. I'm done, I move it to shameful. It's a shameful thing to hear outside. Vertically opposite. Vertically opposite. Yes. When you have continuous line and ascent, they form vertically opposite angles. Do you know what people do now? Is that on the same line? So look at this line continues like this. This one continues like this. Means this angle is also this angle.
so that on the horizontal, like the total will be vertical. So on the horizontal, we have another 5.
Now I'm not working with what?
How will it be vertical?
I didn't put any vertical angle in. This one. Is there a force? This one. This is the horizontal.
This that 0.5 dispatch.
The what?
The resultant 0.5 dispatch.
Which resultant? Okay, you mean this place. That's the resultant. What is that? Have you gotten this force value? You used to get this force value. If I don't believe in you, okay. Now I believe in you, I'm going to show you getting this one. When she's getting this one, I'm going to be getting this one. Start and it's also for you loud. You see? Yes.
This one, for the first day, yeah, 1 is 750.
What's the
750. You know, for that was this 3 and 5.
But I'm getting this force.
Yeah.
Is this one or this one? Additionally, if you get this one, you already got this one. So I believe this one is the same value. Why? It's the same now, this is the same distance. The only person that will be different is this. Because actually, they have the same charge. Same charge. Which one? So what am I writing as the value? And Z is also
0, 5.
so what's this one? Did you convert to microfarad?
Yes, sir. But last one, you want 0.254.
This one makes sense. Is that the longer distance and the inverse relationship? Makes sense. So we have our vectors now. So let's resolve. Start from here. Y is what? Here is what? 0. This one is what? Here is what? This one. This one that told me 0.25. How did you get it? This 3. I've not resolved it, I've resolved this and this. This one is supposed to be minus.
Therefore, 1 thing. Yeah, 0.33. 0.22. I is equals to 0.467. 67. Then, start with 5.
What's the answer?
That is 25. What's up? What the X and Y of the gap? Positive.
Which one?
The X and Y of the gap.
Is it positive?
You have just 45 is in the first one.
Yes. I was looking at this minus. The answer will be 5. I like this one. 3-point charges are placed at the following. 3-point charges are placed at the following locations on the x-axis. Plus 2 microcoulomb at plus 2 microcoulomb at 0, minus 3 microcoulomb at
And 3 microcoulomb
x equal to 40 centimeter. At x equal to 40 centimeter. Minus 5 microcoulomb at x equals to 120 centimeter.
So what are you finding?
Find the force on the -3 microcoulomb charge.
Find the force
On the -3 microcoulomb charge. Other ones. Which one? Which one? Any question?
3-point charges are placed at the following: +2 microcoulomb at 0, -3 microcoulomb at x equals to 40 centimeter, and -5 microcoulomb at x equals to 120 centimeter. Find the force of the -3 microcoulomb charge.
So what do you notice about all of them? They are on the rear. What do you notice about all the charges? Where is all of their location? They are collinear vectors. They are one of the same examples. How do you know that?
What is Z?
But the question is unfair.
Also, to be on either side, you are sure maybe
Anyway,
either side should be here and then
okay, why? That negative is talking about their charge, their polarity, their position. They wrote them separately. If their position, they would have written it x -2. Yes. Read it out for me.
you want charges is at the following: +2 microcoulomb at 0,
+2 microcoulomb at what?
at 0,
At 0. Uh-huh. Uh-huh.
-3 microcoulomb at x equals to 40.
X equals 40. Minus what microcoulomb?
-3
At position 40, abi?
yes, and -5 at position 120.
Minus something, abi?
-5.
Then say fine.
On the -3 microcoulomb.
I shall know that this one, the positive charge will be pulling him like this.
Yes.
This one will even be repelling brother again. So you need to find this value of this, find the value of this. Since they are collinear, you don't need all these, add them up together.
Yeah, but you find the
You will find this force, the one that is due to this. Find this other one, the one that is due to this. Add them up together. Because the vectors are acting towards the same direction. They're acting towards the same direction.
one was coming this one, one was coming
Wait,
this
the
one.
mic is not working. The battery of the mic.
That's stopped the battery.
All right. If you ever get the topic, just watch it. I just hope that one is that's.
So sharp. Yes. Ah, this sweet. Something. After so, what's that?
All right. I'm teaching you. There's no much. Active. All right, so
Okay, sir.
value.
I'm coming.
After the doing sheets, see how comfortable you are. Oh yeah, now values.
Who is causing this one?
Body,
Uh,
2 microcolumn 193, that's 0.3375. For the second one, that is the 500, we have 0.09375. So the next cost is going to be 0.431. 0.43125. Next question, sir.
like the spirit. Like the spirit. Next question. A charge of +6 microcoulomb experiences a force of 2.0 millinewton.
Okay.
In the positive x direction at a certain point in space. A. What was the electric field? At what was the electric field at that point before the charge was placed there? You must take back the hand.
Was
B. Describe the force. Describe the force. -2. Describe the force A -2 microcoulomb charge would experience if it were used instead of the +6.
because someone did not. What it was?
A charge of +6. This was a simple draw. Leave it. What is that? Is the field not going to be 0.73? It will be like 0.73.
Yes.
Then you're not going to that's the whole of us. Then you have to multiply that. So, see, leave it. Leave it. There's no time for busy things like that. And to waste your life doing rubbish.
That's question, sir.
You see what I'm saying? You become. Why are we? What was our mission? And to expose the plans of the devil. Let's try it. I know you will get it. You know that concentration.
Next question.
The tiny sphere. The tiny sphere at the end of the weightless thread illustrated below has a mass of 0.6 gram. Has a mass of 0.6 gram. It is immersed in air. Immersed in air. It was shook in air. You understand?
What should be there?
The shook is air.
Okay, she is one.
And exposed to resultant electrical field and the common yash. And exposed to a horizontal electrical field
Oh,
of strength 700 Newton per coulomb.
I can't hear you, sir.
Of strength 700 Newton per coulomb.
I can't hear you, sir.
Of strength 700 Newton per
I
coulomb.
can't hear you, sir.
Skip. Just stop. I just get you.
I can't hear you.
700 Newton per coulomb. The ball is in equilibrium. What are the magnitude and sign of the charge on the ball?
The magnitude.
Like, when you read that, see it.
So deal. Listen. No go far.
So,
Yes.
talking about, I would find it for some last time definition.
No, let me tell you this myself.
Okay, so find it.
Do it too. What would you have done in my absence? I want to see it. Who has to do it? Now, this is what I'm teaching this one. What did you do now? Since you skip the question. I cannot, she cannot be the one that puts all these ones. The line. I'm out. Now, she's not doing anything. She's still with the problem. I mean, I am a train. And let's busy. I shouldn't work. And I waiting to keep battery. All the good food I've eaten, not video. Chill life. This is the question. This is the question.
I know. I got to my nose okay.
You two get out of yourself.
Sure, I know. I don't know for the question. No. I got to my Happy Council. Let's solve this. But then,
Okay, so where's the question answer?
said at the end of the witness prayer, illustrated below, has a mass of 0.6 grams. It is immersed in air to a horizontal electric field of strength 700 newton per coulomb. The ball is in equilibrium. What is the magnitude assigned on the charge of the ball? A tiny sphere at the end of the witness thread, illustrated below, has a mass of 0.6 grams. It was immersed in air to a horizontal electric field of mass 700 newton per coulomb. The ball is in equilibrium. What is the magnitude assigned on the charge of the ball?
So what's the question? How did this guy get here? If this is really wrong. Understand? It brings us towards the point of question. So we understand that the problem is not solved. So you have to try something. So all we're going to do is this guy is a field. I know that when you have a field, right? You have a field. First, our unit was charge. Because this is the charge of a mass.
The mass.
There are no charges here.
Particularly charge
Of what?
of the ball.
That means it is the charge.
That's the mass.
The mass, a charge has this.
And that's the mass of the charge.
So then this thing is a charge too.
Okay.
But we don't know if it's more negative.
What's it there?
But we know that the field that is approaching it, the field that is coming from a positive charge. Because it's approaching zero. Maybe from something towards zero. That makes us even get a bit of convention that is there likely to be a negative charge. We cannot conclude. So first thing first, we are going to do, we have to resolve. That is what we can do. And if this was a simple harmonic motion,
I would take the yoga, but we can do it in
we must change it.
nothing.
So, we said the tiny sphere at the end of the week illustrated like this has a mass of 0.60 gram. It is immersed in air and exposed to a horizontal electric field of strength.
700 years ago.
Okay.
The ball is in equilibrium. What is the magnitude?
The ball is the equilibrium. And
What is the magnitude assigned on the charge of the ball? And then we are giving the diagram.
that means even when the ball is like this, it's actually comfortable. That tells you that truly, for this ball to be actually wrong here, wherever this field is coming from, the positive charge.
Okay.
And this guy is comfortable with that field. Just opposite. Just opposite.
Yes, sir.
So we know that the charge of this thing is what? It's a negative charge.
Okay.
It's receiving the field. What is it? Yes, it's receiving the field. Understand? If you didn't receive the field, it would have swung back
to
to the side. But they said it had to come like this, and it balanced like this. Obviously, there was a force that kept it balanced. There's a force pulling in this way, right? That is negating the effect of the restoring force. I need to bring it to the actual equilibrium. You get it? Sorry. You know, there's a tension here normally. Tension T.
well, is the weight because of the tension?
It what?
The weight. You said it was a weight up and downward.
It's normally, it's going to experience the weight acting downward. You know, this is going to be 0 points.
6.
That's the weight.
Yeah.
Weight.
So
It
the
is
tension is greater than the weight of the
This is T. We can resolve this to know what is here. Can balances this one. And we can now know what is here. And that value that is here exposes the force that is bringing this electric field. Because that force that made these guys that to go here. And that force had to balance with this force. Who is the force that is there? The what component of this? See something. If here is 20, here is what? If I'm resolving a vector to this place, when the angle is here, line this vector, means this one now will be the 20 cos theta. Maybe we can thought is sine, it's not sine because the angle is not to the result now. The angle is not better. So 20 cos.
How do you not the results now?
I don't know. It's the same thing you get as an answer. Which one? So let's say you answer that time. So from here now, I'm going to be having what? 80, right? Sorry. We don't need this angle again. This is 20. This is 20. So it's here is 20 cos theta. How many years old? It says in answer is 20, this one. See the alternating angle. Alternating angle, see. So if here is 20, here is 20. Z, and use Z or Z. So here is now what? There's 20 sine what? Sorry, T sine T cos 20, and here is T sine 20. Do you get that? So once we can get the tension, and Wala is having solved. You get now. So how do we get that tension? Then we know sum of upward forces must be equal to the sum of what? So we can explore it. So we can see T cos 20 is supposed to be equal to 0.006. What's cos 20?
0.9396.
Oh yeah, we'll see. 0.what?
396.
And so what does it give us? When you divide?
It gives us 0.00638.
0.00638 Newton. That's the tension in the rope. 0.00638. What's this side?
The casual side.
I don't know, put tension on this whole place says what? 0.00638 sine 20. What's the answer?
It gives 0.00218.
0.00218. Now, you cannot get what this place was. The force that was on this guy here. You can get it. What is the question asked us to actually find?
The charge.
The charge, I mean, we already know the electric field. Once we know the force, we can get the charge. So, we already know the force. What's the force? The total force acting here has to be the same acting here. So the force acting here is what?
0.00.
That the force of that charge that was bringing here was 0.00218. So therefore, we got the force, we know the charge, and we know that E is equal to F over Q. Q is equal to F over E. Q is now equal to 0.00218 divided by 700.
Yeah, 3.117 times 10 is power minus 6.
3.117 times 10
is power minus 6.
of microcoulomb.
The world was pushing the philosophy of suction.
It does not interest.
Was not actually.
Would be interesting now. We'll start doing things on things. Just we'll start as a boundary portion. We'll know that this is what is maximum pressure energy. I don't know that very GH.
So what if we don't use like a smooth ground moving on? We have verticality and height. We find acceleration.
Okay. So this next question. Write this down. Charges plus 2, plus 3, and minus 8 microcoulomb. Charges plus 2, plus 3, and minus 8 microcoulomb are placed in the air at the vertices of an equilateral triangle of side 10 centimeter. Calculate the magnitude of the force acting on G. Calculate the magnitude of the force acting on G minus 8 microcoulomb charge due to the other two charges.
What's this one?
Equilateral triangle side 10 centimeter.
Okay.